Hello students. So this is our second session of the chemistry. So today we will study about the D and F block elements and the coordination compound together. So let's see today what we will study. That is first it is D and F block. D and F block element and their properties. Okay. Second it is coordination compound. So coordination compound it is the second topic we will do. Okay. Next, it is some questions we will do topic wise. That is topic wise PYQ. So this is our today motto to do D block and F block elements, coordination compound, and some questions based on them. So starting with the D block element. So we will study D and F block separately. First, we will start that is a D block elements. So in case of a D block element, this it is positioned in between the S and P block elements. So between the S and P block elements, D block elements it is there, and it's from group number 12 to from group number 3, from group number 3rd to 12th group it is D block elements are there. Okay, so these elements are also known as a transition metal. So let's see what is the definition of transition metals. So basically, transition metals are what? It is those metals which is lies between the S and P block elements. Those elements which lies between that properties also which elements whose properties lies between S and P block element. So generally this is a definition it is a used, that is those elements which lies between the S and P block elements. So it is not a fit for all the elements. So the new definition it is what? New definition. Once again, let me. Yes. So what is the new definition of transition metals? So basically, those metals which have partially filled d orbitals, those metals which those metals or elements, those metals or elements which have partially filled, which have partially filled d orbitals. So these are the definition. This is the definition, a new definition according for a transition metals. Those metals which is having a partially filled, that means it is a D1 to D9 we can have. If it is a N, this is also we can do in all the in ground state, in a ground state, and its common oxidation state. Common oxidation state. Basically, this should be partially filled d orbital in its ground state as well as in its common oxidation state. For example, if it is a zinc, it is a given to us. So, is it a transition metal or not? How to check it? So, let's see. First of all, what is the configuration of a zinc? In a ground state, it is a 4s2 3d10, 4s2 3d10. That means d orbital it is a fully filled. So we cannot say it is a. So let's check for the other oxidation states also. That common oxidation state of a zinc it is a 2 plus. So if we find the configuration of this, it is a 3d10. So again we can say the orbital, it is a d orbital, it is what, fully filled in a ground state as well as in a common oxidation state. So I can say zinc is not transition metal. So that means all the elements which is fully filled in its ground state and common oxidation state, then we can say they are not a transition metals. And we can say all the d block elements, all the d block elements all d block elements or transition metals, either we can say transition element or transition elements, except group 12 element. Group 12 element means zinc, cadmium, mercury, and the last element Cn, that is also 112, atomic number 112, and Bm. So these are the this is a note point we should learn for the transition element. The transition elements are all the d block elements, okay, except the group number 12. So let's see the electronic configuration of d block elements now. So general electronic configuration, it is what, n minus 1, d 1 to 10, and s 1 to 10, 1 to 2. That means d, it can be 1 to 10. Either it is in some cases, if we are excluding that pd, it is this configuration. If we are including pd, then we can say it is n minus 1, d I can put, that is a 0 to 10, and s 1 or 2. So this is a outermost cell configuration of a d block element. So let's see for the 3D series. So there are four 3D series, four series are there. First, this is a first transition series, transition metal series. Either we can say this is a 3D series, 4D series. This is a 4D series. Next one, it is a 5D series, 6D series. Basically, the period number also we can say it is a, this one, it is a fourth period. This is a fifth period. Sixth period, it is a, okay. So similarly, we can say it is a seventh period. So in case of a configuration, if we are writing the configuration, this is a, we can say S and 4s, and in case of a 3D series, in case of a 3D series, the electrons, last electron will go in the 3D series. So 4s, it is always, generally it is a 4s, it is a fully filled, that is a 2 electrons. So where it is a exception is, it is there, that is a chromium, and in case of a copper, it is a exception is there due to the fully filled and half filled orbital, it is a more stable, okay. So in case of a chromium and copper, it is a fully filled, half filled and fully filled configuration, it is a getting, that is a more stable than the other partially filled configurations. So here it is a S will be 4s in the case 4s, that we can say S will be 1 in case of a chromium, copper. Other elements are there in case of a 4D series. There is a elements from the niobium, that is a S is equal to S, it is a 1 in all the elements. Palladium, it is a different, where S it is a getting 0. Only it is a one element is there in which S it is a 0 and D it is a 10. Okay, this is also due to the what, that it is a getting fully filled fully filled configuration, which is more stable. And other cases, it is a why it is there. So what is the reason behind this? That we can say it is a one electron it is there. In this cases, in case of a platinum, it is also one it is there. Okay. Copper, Ag, Au, it is also having a one electron in a s orbital. Okay, so this all group it is a having this all group it is a 11th group, which is having a one electron in a s orbital. So this is a case where it is a one orbital. So in case of a 3D, it is this copper chromium. In case of a 4D, it is a from the niobium to palladium. It is a one, and it is a another. It is a silver. So what is the reason behind this? So due to first reason, we can say the stability of orbitals. It is getting stabilized by half filled and fully filled. So half filled, and fully filled. Fully filled. It is a configuration. These are the two reasons. One another reason, that is a transfer of electrons occurs between the s and d orbital. Why it is so? Since it is a small energy gap, small energy difference, small energy difference between ns and n minus 1d or orbitals. So basically, there is a very little difference, energy difference between the ns and n minus 1 d orbitals. That's why it is a electron transfer occurs easily to get stability. So the all exception I have written in a one table, that is a in case of a 3D, the exception it is a with copper and chromium. In case of a 3D, it is a copper and chromium, in which it is a one electron in a s orbital. Other it is a case of 4D, it is there this one. Case of 5D, it is this, and 6D, it is this. Lanthanum and actinium, it is also having exception. Why it is so? Since 4f electron, it is 4f orbital, it is also there, and this is not filled first. It is a filled. It should be filled first, and it is we can see this is not filled here first. So that's why it is also exceptions of Hund's rule. Hund's rule exception, we can say Hund's rule exceptions. So what are the elements which have a Hund's rule exception? So this table it is given all S1 and S0, along with that actinum and lanthanum. So these all have a Hund's rule exception, in which we know it is electrons should be filled in the increasing order of energy. So here it is a invalid of that Hund's rule. Next, it is a general properties of the transition elements. So what are the properties, general properties that we can say? First is starting with the physical properties. First, it is a size of atoms, and it can be metallic size or atomic size. So if we see it is the size, it is in case of across the period, size it is a decreases. Across the period, what it is a factor we apply, that z effective increases. If z effective increases, overall the force of attraction on the electron it is increases. Due to that, size it is a decreases, that we know. So let's start with the 3D series. In case of a 3D series, we have a scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So in all the elements, we know it is in general what happens, the size decreases, and up to this it is correct. But after that, what happens, basically it is electron repulsion in the d orbitals. So d orbital electron repulsion, it is a nearly same than the attraction, that is a Z effective. So we can say it is a order, it is a this. Now why it is so? Here it is a attraction is a dominating than the repulsion. In case of ferrous, cobalt, nickel, it is a attraction is basically overcoming to the repulsion, and after that repulsion is a dominating factor than attraction. In that case we can say if repulsion is of electron it is there, so they will the size will be increases in this case. Okay, so zinc, it is a more in size than the copper. Next it is a down the group, we can talk down the group. So down the group we have a 3D series, 4D series, 5D series. So these are the series, and it is a element is it is a started with the scandium, then titanium. Down the group we have a scandium, yttrium, lanthanum. Here it is a zirconium and hafnium. So in case of down the group, atomic size it should be increased. As we move down the group, the number of cells increases, so size should be increase. So it is a normal for the third group. After the third group, it is a size increases, then it is also similar to the 3D, 4D and 5D, it is getting similar due to the lengthenite contraction. We can say this is a 3D, it is less than the 4D, and 4D it is basically it is nearly approximately it is equal to the 5D. Why it is so? That is reason it is a lengthenite contraction, we can say. Lengthenite contraction when the d orbitals and f orbital comes, in that case it is a size decreases. Okay, let's see the question, it is a given also. So the zirconium and hafnium have a similar atomic and ionic radii because of reason it is a given. So what are the reasons for the zirconium and hafnium? It is a size similar, so having a similar chemical property, belonging to the same group, it is having a diagonal relationship, it is a lengthenite contraction. So this is our correct answer as we have seen just now. So it is a PYQ we are doing. After each topic we will do the PYQ. So lengthenite contraction, it is there, it is a reason for the decrease in the size. It is comparable to the 3D 4D series. Next it is a ionization energy. So ionization energy, it is a, we can say first it is a for first across the period, so across the period ionization energy, it should be across the period, as we know Z effective it is increases, so ionization energy should decrease, sorry, it will also increase as a Z effective it is increases, the force of attraction on the last electron it is increases. So due to that we can say here it is the ionization energy or enthalpy will increase. So across the period, if I say it is a 3D series, if it is a 3D series, in case of a 3D series it is a scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So as we know the the ionization enthalpy it should be increases as we move. So this should be our order. This should be our order of ionization energy. but the order it is a not a this. Why it is so? There is a repulsion and extra stability it is a getting. So we can say the order it is a, you can remember by this, that is a, just take a, here it is at a second position, sixth position and seventh position, the order will be opposite of a, that regular order. So what is the regular order? This is the first, second at a second point we, so the, this is a, our change we can do at a second position, at a second position should be changed. So this and this is the first, second, third, fourth, fifth, sixth. At the sixth and seventh it will be opposite, otherwise it is a, all order will be same. So this is a ionization energy. First it is a, we are talking about first ionization energy of all the elements. So the final order will be what? It is a scandium, titanium, then vanadium, then it is a chromium, manganese, iron, cobalt, nickel, copper, zinc. So this is the first ionization energy of all the elements, 3D elements. Okay. Down the group, if I say down the group, so down the group, as we know, number of cells increases. If number of cells increases, the ionization energy will decrease. So the normal orders would be what? It is a 3D, then 4D, then 5D. But this order it is not followed, as there is an exception. We can say it is due to the lengthenite contraction, that is a order will be 5D, will be more than 4D, then 3D. Okay, this is the order it we can follow. It is there. So that is a ionization energy of 3D elements and down the group. Next, it is a property we can see, that is a catalytic property of D block elements. So D block, since D block elements have a variable valencies and they have a large surface area also. Metal have a, due to large surface area, so they have a large surface area also. So due to that we can say its catalytic property will be more. So due to the presence of free valencies and also they have a variable oxidation state, due to that it is having a catalytic property. So what is a catalytic property? Basically they provide a surface for the any reaction, and for example it is a hydrogenation, it is a given. So this is a alkene. So when it is a hydrogen gas, it is attached with the this, so they will be hydrogenated and hydrogen will be added. So basically they provide a surface for the reaction. So what catalyst we can take? In case of this we can take a platinum, a nickel, or a palladium. Okay, this type of metals work as a catalyst. So another example which is a very important, and it is a given in the NCERT. So what is the reaction? Here it is a given that iodide it is converted into iodine, and this is sulfate, it is given converted into the sulfate. So what happens basically, Fe2 plus here it is used, and as we know the catalyst work as a what, it is involved in the reaction or not, that we can say it just involved in reaction. After the reaction it is getting separated from the reaction. So there is no role of a catalyst in the final reaction. In the final reaction there is no role of a catalyst. So in this reaction we can say Fe3 plus it is appeared and disappeared. So we can say this is a Fe3 plus. Here in this case it is a catalytic property it is showing, which is conducting this reaction. Other catalyst it is we use generally, that is Fe, that iron we use in the Haber's process. in the manufacturing of ammonia gas. V2O5, which is used in the contact process for the formation of SO3 gas, we can say it is a H2SO4 acid. Platinum, it is used for the Ostwald process for the nitric acid formation, and nickel, it is used for the hydrogenation of ions. Okay, that hydrogenation means that we have converted an unsaturated compounds into the saturated compounds. Next, it is a question we can see to choose the correct answer from the given below. So first list one, it is a given, the some process it is a given, and the second list it is a given that catalysts. So Haber's process, as we know, it is a use of Fe catalyst, it is there. Weber's oxidation, it is a PdCl2, so that you can remember it is from the organic chemistry. Wilkinson's catalyst, that is also this, it is a triphosphine, and RSCl, this is a catalyst. Ziegler catalyst, that is a TCl4 with that Al trialkyl, we can take it as a trialkyl. So this is a what a Ziegler-Natta catalyst we it also call. So we can say the first it is a matched with the first, second it is matched with the second. So the answer it is our first answer, it is option is a correct. Next topic we can take, that is fourth property, that is a alloy formation. Since the metals having a similar size, so they have a similar size. And what is the alloy? Basically it is a solid solutions, it is a homogeneous mixture of two solids. So it is a solid solutions which form a homogeneous mixture, and in this case we can say they can be mixed only mixing of metals occurs when size difference we can say size difference is less than 15%. If it is there less than 15%, we can say they can form alloy. So basically they must have a similar size. If it is not in a similar size, so some examples we can remember, that is this first two example, it is a very important, bronze and brass. So bronze we can remember it is a jade, it is there. So in the compound mixture, it is jade is not zinc is not there. So N will be there, Sn will be there, that is a tin. So copper plus tin, it is a what, bronze. And if it is a brass, it is a given, we can say as it is a there, we can say tin will be not there, and the copper with zinc it forms one brass. Other example, that is a amalgam. It is also a special type of alloy which is formed by the semi-solid alloy, which is formed by what, it is a mixing of a metal with any metal we can take with a mercury. So if any metal it is a given with mercury, they form what, amalgam. So they form amalgam. So this amalgam can be formed only with those metals which have a similar size with the Hg. If it is a cobalt, iron, nickel, it is a given, they will not form amalgam as they are in a large difference with the mercury. Okay, so the what is the important point for the alloy? It is a size difference should be similar, we can say size difference should not have a large. Okay, next it is a industrial compounds, those compounds which is formed by the adding a small amount of hydrogen, carbon, nitrogen, and we can take boron also. So these are the non-metals. So these non-metals we can take non-metals when it is trapped in the metal crystal. So when it is trapped inside the crystal lattice of a metal, they form a what, industrial compound, and they generally form what, non-stoichiometric compounds. Non-stoichiometric compounds like it is a BH 0.56. This is a TIH 1.7. So it is in decimal form. It is not in a whole number, and also it is depends on the solid lattice also. Okay, this is all about the solid state. They retain the metallic conductivity. They have a high melting point than the pure metal itself. They are also very hard as some industrial compounds, some non-metal it is added. So they basically occupy the voids of. For example, one lattice it is a given, and in this lattice, if we fill the voids with some non-metal elements, so what will happen basically? The packing friction will increases, and its melting point it is also increases. So these are the what non-metals we are adding. So they will form what industrial compound. They are also chemically inert. So they are chemically inert as it is a mixture of a compounds. Okay, they are not a pure now. Okay, so this is a industrial compound. Next property of a D block element, it is a melting point of a D block elements. Melting point basically depends on a melting point basically depends on what that number of unpaired electron. Number of unpaired electron. As the number of unpaired electron it is increases, the metallic bonding also increases. So number of unpaired electron it depends on what basically melting point depends on the metallic bonding. Metallic bonding. And metallic bonding basically depends on the number of bond. Metallic bonding means that metal, the bond between the metal and metal it is a formed. So which depends on what? That number of unpaired electron. Okay. So across the period what will happen? So across the period, zinc, cadmium, mercury, they will have a zinc, cadmium, mercury. It will have a list. We can say they have a lowest melting point in respective series. In respective series. So zinc it is from the 3D series. So in 3D series it is the lowest melting point for the zinc. So here we can say somewhere it is a zinc will be there. Zinc it is there. So this is for the 3D series. This is for a 4D series. This one it is a for a 5D series. So in each of our series we can say the lowest melting point it is a for the it is a last element 12th group element, that is a zinc, cadmium, mercury. Why it is so? As we know, in case of a zinc, cadmium, mercury, the unpaired electron will be 0. Unpaired electron will be 0. Second thing, it is about chromium, molybdenum and tungsten. They are all highest. They are highest. Why it is the highest? As we can see, the manganese it is having a highest number of lone unpaired electron. So why it is not a manganese it is having a highest melting point. So basically reason it is there. Manganese it is there. So which is not getting a not having a highest melting point. Even though this manganese it is having a highest number of unpaired electron. So basically this forms a manganese forms a what 3d5 d5 configuration. It is a very stable. Since this is a stable configuration it is a forming, this will do not form a what that metal bond. So in this case we can say The chromium, it is the what? Highest. Chromium, it is the highest. Chromium, molybdenum, and tungsten. Highest melting point in a respective series. Okay. Next, it is a lowest melting point among all the D block element. It is a zinc. So since zinc, it is also exist in the liquid state. Liquid state at a room temperature. So at room temperature, it exists in a liquid state. So we can say its melting point, it will be very low, that is a minus 38 degrees Celsius. Highest melting point of tungsten, it is there, that we can see here, it is the highest among all the D block elements. So that is a 3400 degrees Celsius, which is also used in the nichrome wire, which is a heating elements also, that is tungsten is used. Next, down the group, it is a melting point, it is a increases as we move down the group. Down the group, it is a melting point increases generally. Melting point increases generally. So in case of this, it is a not increases. So these are the exceptions where we can say this should be remembered. So zinc, it is a more than the cadmium than mercury. So mercury, it is a list. That also we have remembered, that is a list of D block elements, it is a mercury. So mercury, it is having a list melting point. Next, it is a out of a copper, silver and gold, it is a copper, it is a highest, then silver, it is a lowest. So that we can say it is a irregularity in the trend, it is a there, so that we can remember. Next property, it is a enthalpy of atomization. So what is the enthalpy of atomization? So basically the energy which is required to separate the metal atoms from the metal lattice. So metal crystal lattice is there. So we have to separate into the gaseous atoms. So if it is a metal solid, it is there. If we convert into the metal gaseous atom, then it is known as a delta H atomization. Then we can say it is a this energy which whatever it is required is known as a delta H atomization. Okay, this is also known as a delta H sublimation. We can say it is also same as a delta H sublimation is known as what? When solid element, it is converted into the gaseous element. So in this case, we can say first it is in a 3D series. In 3D series, the it so basically, first of all, what are the factors we can say? It depends on the delta H atomization is directly proportional to the what? It is a melting point. Either we can say metallic bonding. So stronger will be the metallic bonding, the delta H atomization will be more. So here why it is we can say maximum, it is in the 3D, it is a vanadium. So it is a data based, we can say it is given in the NCERT that highest it is for the vanadium. So in case of a 3D series, vanadium, it is having highest, it is not a chromium. So the in case of a 3D, highest it is a highest for a vanadium. So this we can remember only where it is a metal bond we are breaking to get a gaseous atoms. Next property, it is a density of a 3D elements. Density of a 3D elements, it depends on the what? That we know it is a if so density, it is a as we move from left to right, it is a increases, density basically increases, and as we go down the group, it is also increases. So from top to bottom also it is increases, and somewhere it is also same, we can say scandium, it is less than titanium, vanadium, chromium, manganese, it is increases. But in case of nickel chromium, nickel copper, it is the same, and zinc it is less. Why it is so? Zinc is a less, that we can say zinc is having a lower density because of its higher large atomic volume it is there. So minimum density in 3D series it is a scandium, and maximum density in 3D series it is we can say nickel or copper. Down the group it is a what? 5D it is a larger than the 4D, then 3D. There is no exception. Next, it is elements with the highest density among all the D block element, that is osmium or iridium. Out of osmium, iridium, it is a higher than osmium. If it is an option, it is a given for the iridium. Take for this iridium. If osmium, it is a given, then osmium, it is our answer. If both it is a given, take for this iridium. Iridium, it is our correct answer for the higher density, highest among the D block. Next, it is a color properties. So color, it is a, and anywhere it is a color, it is a formed, we can say there is a transition between the DD transition will occur. DD transition, basically D orbitals it is there. Suppose I am taking the some element which is having, that we can take it as a T2Z and EZ. So basically electrons get excited and de-excited. On de-excitation, the energy will be released from the compound or element, and the energy which is released on de-excitation, that if it is covering in it lies in the visible range. If it is lies in the visible range, then we can say it is a color will be there. So DD transition is one of the reason for the color in a color in the D block elements, and this it is a color we are checking in the aqueous medium. Aqueous medium we are checking the all the ions. Okay, ions it is in the aqueous medium. Generally colorless for the what it is a, if D it is having a zero unpaired electron, then we can say there is no possibility of a transition of electrons. And also in the case of in case of a D10 also, it is a D transition will not occur, as number of unpaired electron it is a zero. Colored, it can be possibility it is a from D1 to D9. From D1 to D9 it is a possibility of a DD transition is there. Okay, so color of one, it is a generally we can say color of a D, N and D, 10 minus N, it is the same. For example, D10 and D0, color will be same, that is a colorless. For D9 or D1, color will be same. For D8 to D2, color will be same. Mostly it is a followed. If it is not given in the question, we can apply this. Otherwise, this table we should remember, which is given in the NCRT. So this is from the NCRT. This should remember why it is important. It is asked in the exam also. So color less, it is for what? Colorless we can skip, that is a, we know in case of D0 and D10, it is always a colorless. It is always a colorless. Other than that, we can remember this colors with the ions, and it is in a aqueous medium. Aqueous medium, in it is a dissolve in the water. Either it is known as a hydrated ion. Hydrated ion colors, it is a there. Next property, it is a magnetic property. What is a magnetic property? So basically magnetic property can be, magnetic nature of ions can be, it can be paramagnetic, diamagnetic, ferromagnetic. So what is a diamagnetic substances? Paramagnetic substances. So basically those substances which is attracted in a magnetic field. Attracted which is getting attracted in a magnetic field. If it is attracted in a magnetic field, we can say it as a paramagnetic species. Diamagnetic species, those species which is repelled in a magnetic field. Ferromagnetic substances, it is a very important, as we know it is a extreme form of it is a given in the NCERT also. It is an extreme form of paramagnetism. It is an extreme form of paramagnetism. Okay, so attracting, highly attracted in magnetic field, then it is a paramagnetic compound. So we know the one formula for the magnetic moment value, spin only magnetic moment value. It is what? It is a square root of n into n plus 2, where it is a n plus, so where n it is a what? Unpaired electron, where n is a number of unpaired electron. So number of unpaired electron, if it is a 1, we can say magnetic moment value it is a 1.73. If 2, it is a 2.2, 2.83. If it is a 3, then we can say it is a 3.84. If it is a 4, we can say it is a 4 point something, 4 point something. If it is a 5, then we can say 5 point something. So we can check with the help of this also if magnetic moment value it is a given. Next, it is a question. Which of the following pairs of ions will have a same spin only magnetic moment value? With a pair it is a given. First it is a given, that is a Gen 2 plus, titanium 2 plus. In case of a Gen 2 plus, it is a configuration we can find. For a Gen 2 plus, it is a 3d10. Titanium 2 plus, it is a case of a titanium, it is a 4s2, 3d, 3d2, it is a okay. So if 2 electron it is a removed, then we can say this is a d2. Next it is a ions we are having, that is a titanium 3 plus. Titanium 3 plus, it is a d1. Chromium 2 plus, it is a given. In case of a chromium, this is a 3d4. Fe2 plus, it is there. So for the Fe2 plus, we can find the configuration, that is a d6. Okay, this ions configuration we can find, that is a Fe2 plus we have found it. Next it is a vanadium 2 plus, that is a 3d3. Copper 1 plus, it is a 3d10. So in case of this unpaired electron, it is a 0. So pair of element it is a given. So 3d in case of a 3d6, it is a number of unpaired electron we have, that is a 4 unpaired electron. Here it is a 3, here it is a 0. Next it is a 2 unpaired electron, 1 unpaired electron, 4 unpaired electron. So chromium 2 plus and Fe2 plus, it is having a same magnetic moment spin value. Okay, so that we can say it is a what? Correct answer. It is a what? Chromium 2 plus and Fe2 plus. That is a B option is a correct. B, it is a one more, it is a ion, it is there which we have left, that is a Cu2 plus. In case of a Cu2 plus, this is a 3d9, and 3d9 it is having a 1 unpaired electron. So titanium 3 plus and copper 2 plus, it is also having a same magnetic moment value. So then we can say B and C it is a correct. So D option is a correct. Okay, next it is a oxidation state of this d block elements. Since d block elements it is having a variable oxidation state, it shows as we can say this is a ns and n minus 1d electrons, which is having a similar energy, we can say similar energy, and difference it is a very less. In case of this we can say the ns electron and n minus 1d electron, both electrons can be used for the bonding. Since it is a ns and n minus 1d electrons is used for bonding, we can say minimum oxidation state it is a ns, and maximum oxidation state we can have that is a ns electron plus n minus 1d electrons. For example, for a manganese, the configuration it is a 4s2 and 3d5. So in case of for this minimum oxidation state, it is what ns electron. Ns electron means the last cell electrons it is a having 2. So maximum it is a what ns electron, which is having 2 electrons, and plus n minus 1d electron, that is a 5. So which is having a similar energy, we can say both electrons, that is a 7 electrons can be used. So minimum it is a plus 2 and maximum it is a plus 7. So on basis of that we have a one list of oxidation states of all the elements. In case of scandium and zinc, there is only one oxidation state, only one oxidation state exist. Okay, so this is very important. In case of a scandium, only plus 3 it is a exist, and in case of a zinc it is a plus 2 it is a exist. Other for other elements, the oxidation state which is a stable, we can say it is a 4 plus, it is a stable. In case of a vanadium it is a 5 plus, chromium it is a 3 plus and 6 plus, it is a more stable. Manganese it is a plus 2 plus 4 and plus 2 plus 4 and plus 7, it is a stable. Fe2 plus Fe3 plus is a common, not stable. We are not talking about the stability, we are checking for the common oxidation states of elements. For the nickel it is a 2 plus, for copper it is a 2 plus, for zinc it is a 2 plus only, it is there. So variable oxidation state of it is a due to what? It is a due to the less energy difference between the what? It is a ns and n minus 1d orbitals. Okay, this is a ns between the ns and n minus 1d orbitals. So stability depends on what? It depends on the first, it is a half filled, fully filled, and half filled, T2G. So what is a T2G? So T2G orbitals are what? There are three orbitals. We will talk later also. So T2G orbitals, if it is a half filled, then also it is a more stable. Empty, it is a D0. So half filled T2G means it is a D3 configuration is a more stable. Fully filled, that is a D10. Half filled, that is a D5. Second factor, which is a very important, that is a SRP, standard reduction potential, that we will talk later. First of all, we can say this all oxidation states, which is a given here, that is all, it is having a configuration that we can say it is a D0, and which is also known as a pseudo, that we can say it is a inert gas configuration, D0, inert gas configuration. Since they are having inert gas configuration, that's why it is a more stable. In case of D zinc 2 plus, it is a D10 configuration, it is a fully filled, and this configuration is also known as a noble gas, sorry, pseudo, it is a pseudo pseudo inert gas configuration. Pseudo inert gas configuration, it is also more stable in case of Ni2 plus and copper 2 plus. It is so this instability we can explain later. Fe2 plus, it is D6. Here we can say Mn2 plus, it is and Fe4 plus, it is half filled, that is a D5 configuration. That's why it is a more stable. Otherwise, we can see in case of cobalt, cobalt 2 plus, cobalt 2 plus, it is a 3D8. Okay, the other oxidation states, the other oxidation states, we can say it is a stable. Mn4 plus also we can say here it is a, and D, it is having a D3 configuration, and D3 configuration, it is a more stable due to what? It is a half filled T2G that we have talked earlier. So this is the stability we can see here, it is there. Next we can say depends on the SRP value, we will talk. Before that we can see it is a trend in the stability of higher oxidation states of oxides, oxides and highlights also we can say fluorides. So across the period, higher oxidation state stability decreases. So stability of a higher oxidation states, it is a decreases. Higher oxidation state stability, it is a decreases. Next thing, it is a in down the group, it is a higher oxidation state stability increases. So as we move down the group, it is a higher oxidation state stability will be increases. Okay. For example, this is a compound, it is a given. So it is a vanadium 3 plus, chromium, it is a 6 plus. So vanadium, it is a 5 plus. I think it is a 5 plus. Yes, it is a 5 plus. Chromium, it is a 6 plus, and magnesium, it is a 7 plus. So we are going across the period, and if we going across the period, higher oxidation state stability will increases. So stability wise, if we talk stability wise, MnO4 minus is a more stable than chromium 2 dichromate, that is it is a, and the VO2 plus, it is a less stable. If stability it is a given this, then we can say what is the order of oxidizing agent power. What is the order of oxidizing agent power? As we know, the highest oxidation state of Mn in a plus 7, it is a more stable. Then we can say it is a, if it is a more stable, they will not get reduced easily. In case of vanadium 5 plus, it will get reduced easily. So we can say the oxidizing power of chromium is more than the chromium plus 6 is more than the, so we can say here it is a chromium plus 6, it is a more oxidizing power than the magnesium 7. So this we can say stability of stability and oxidizing power. Next, it is a standard electrode potential trend, that is we can talk here, it is a SRP value. So depending on the SRP value, we can now check for the stability. So as first we can talk about that Mn2 plus to Mn, it is the value, it is SRP value. SRP value, it is increases for Mn, for metal 2 plus 2 metal, it is getting reduction. So in case of this reduction, if it is getting increases, if it is increases, that we can see it is increases as we move across the period. As we move across the period, it is increases, and it is also positive for the copper. And all the cases it is a negative, but for the copper it is a positive. So if it is a positive, SRP value, it is a positive for the copper 2 plus to copper change. For this change, SRP value, it is a positive. If it is a positive, that means this reaction, it is a, this process, it is a feasible. SRP value, it is a positive, that means this is a feasible. Whatever it is a process, it is a given, this is a feasible. If it is a feasible, we can say this, it is a copper reduction, it is a feasible. Reduction of a copper 2 plus to copper, it is a feasible. As we can see here, it is a copper, it is a more stable than the copper 2 plus. Now other cases, we can say it is a, there is a change in the change, it is a given. For that, we can say Mn 3 plus to Mn 2 plus, Mn 3 plus to Mn 2 plus. In case of this, we can say it is also increases, but for 3 values, it is a, for titanium, vanadium, chromium, it is a negative. For Mn, for Mn, Fe and cobalt, it is a positive. So here we can say scandium, it is not given, titanium, vanadium, chromium. For this, it is a SRV value, it is a positive, so it is a negative. For second, it is a Mn, Fe and cobalt, it is a given positive value. Since it is a SRP value, it is a positive. So if SRP value, it is a positive, that means what, it is a, the reduction, it is a getting a more feasible. For Mn, sorry, for M2 plus to M3 plus to M2 plus, means conversion of M3 plus to M2 plus, it is a feasible. In case of this, that we can say Mn2 plus, Mn2 plus is a more stable than the Mn3 plus. Fe2 plus, Fe2 plus is a more stable than the Fe3 plus. And CO2 plus is a more stable than the CO3 plus. So this is the important points we can conclude from the SRP value. Similarly, we can use here also, that is a titanium 3 plus is a more stable than the titanium 2 plus. Chromium 3 plus is a more stable than the chromium 2 plus. So in case of if SRP is a negative, if SRP it is a negative, reduction standard reduction potential, it is a negative, that means the higher oxidation state will be more stable. In case of it is a positive, this we can say the lower oxidation state, it is a more stable. If it is a Mn2 plus is a more stable than Mn3 plus, we can say if Mn2 plus is a more stable, then if I say it is Mn3 plus, it is a more less stable. If it is a less stable, it want to convert into what, Mn2 plus. If it is getting converted into Mn2 plus, that means reduction of Mn. If reduction of Mn it is there, we can say they will oxidize some other, so they will also known as a oxidizing agent. This all are what, oxidizing agent. In case of this, they are getting converted into oxidation. Titanium 2 plus will get converted into titanium 3 plus, that means it is a oxidation of a titanium itself, it is a happens, then we can say this is a reducing agent. So in case of a negative value, the lower one will be less stable, and less stable lower one, it is a, then we can say it is a reducing agent. If it is a higher oxidation state, is a less stable, then we can say it is a oxidizing agent. That point we can remember, that is a very important, that is a, if I can say it is a lower oxidation state stability is unstable. If it is unstable, Lower one, if it is a unstable, then it will work as a reducing agent. If higher oxidation state, it is unstable, then we can say it is a oxidizing agent. So this we can remember. Next thing, it is a, which is an important one from the SRP values. So question, it is asked like this, that is a copper 1 plus and copper 2 plus. Which one is the more stable? Copper plus 1 and copper 2 plus. Which is the more stable? So that we can see which is more stable. You can say it is for the from the configuration wise, if you see, it is a 3D 10 and this it is a 3D 9. Since D10 it is a more stable than this one, we can say stability should be this, but it is a wrong. Why it is a wrong? Let's see. As we know, it is a metal is a converted into oxidized state, that is a, suppose it is a metal plus gaseous ion, sorry, aqueous ion. So this it is given to us. Now first of all, what will happen? This first of all, metal will be converted into the metal gases, and that requires a what energy? That is a delta H atomization. And this gaseous atoms requires some ionization energy, that is also positive. This was a positive. Next, after that removal of electron, that is a what? Formation of a metal ion, metal cation, and this will get into aqueous form. So in case of this, it is a release of a hydration energy. So if there is a solvation of a gaseous metal ion, that energy will be released, that is known as a hydration energy. In case of a copper 2 plus, copper 1 plus and 2 plus, for the copper 2 plus, it is a hydration energy is a high. Hydration energy, if it is a higher, we can say the process of that delta H oxidation will be more. If oxidation delta H it is a less, we can say, then it is a process will be more easy, and for this copper 2 plus, it is a hydration energy, it is a very high. It means released energy will be high. So copper 2 plus, it is a more stable. The question is also there, that is a the stability of a copper 2 plus is a more stable than the copper plus 1 salts in the aqueous solution is a due to what? That we know, it is in case of a copper 1 and copper 2 plus. For the copper 2 plus, it is a hydration energy will be higher, and enthalpy of atomization, it is incorrect, that we can say the hydration energy will be very high for the copper 2 plus. That's why it is a more stable, even though it is having a fully filled configuration. Next, it is this the anode value of for the Mn3 plus to Mn2 plus copper, it is a more positive than the that of chromium 3 plus to chromium 2 plus, or Fe3 plus to Fe2 plus, is due to the change of what? So in case of Mn3 plus, in case of Mn3 plus to Mn2 plus, what is happening basically? It is why it is positive, more positive than the chromium 1. Why it is a more positive? Then we can say it is a configuration of Mn3 plus. What is the configuration of Mn3 plus? It is a D, it is a T4 configuration, and if we remove one electron, or if we add one electron, what will happen? This will get a D5 configuration. So D5 configuration is a more stable. Since this is a more stable configuration, that's why we can say it is having a positive value for a E0 value, means SRP value will be positive for this. The reason is what? From to change of a configuration from D4 to D5, it is there. Okay, so our answer is about C option is the correct. Okay, let's see some other compounds, that is some important compounds of the transition elements. First, we can say it is oxides and oxo anions of metals. So, oxides of metal, it can be basic, it can be acidic or amphoteric. So, acidic, so it can be basic, acidic, either we can say first amphoteric and acidic. So, it can be basic in case of a +1, +2, +3, amphoteric in case of +4, and +6, +5, +5, +6, +7, it is acidic. So as we know, it is a amphoteric oxides. This we have to remember. In case of this all oxides are what amphoteric, which is very important for exam. For all the inorganic compounds of oxides, these oxides will be all the oxides of a Zn will be amphoteric in nature. Amphoterics are those oxides which can react with the acid as well as a base. So beryllium, it is a BeO. Gallium, it is aluminum, it is Al2O3. Gallium, it is a gallium, it is a O3. That all it is a given here. It is a amphoteric in nature. So if it is a given, that is a CrO3. So what is the nature of a CrO3? What is the nature of a CrO3? If we check for the oxidation state of a CrO3, chromium, and this we can say here it is a oxidation state of a chromium will be +6, and +6 it is not for the amphoteric. For amphoteric it is a +3. If it is not in this list, then we can follow this one. So this rule, it is only valid after this list. It is a given for the amphoteric. So amphoteric, it is a only in case of a +3. It is a +6. +6 for this we can say it is a acidic in nature. So this is a acidic. Suppose it is a given, that is a CrO2. CrO2, it is a what, +4. So CrO2, it is not there. Suppose it is a CrO, it is a given. So it is a +2. We can say it is a +2. It is a what, basic in nature. So in this way we can find the nature of oxides and oxide anions. In case of vanadium, it is a given in the NCERT also. Vanadium with the acid, it gives a what, vanadium. In case of it is giving VO2 plus, that it is a oxidation state will be +5, and with the base it gives what, it is a oxidation state. If we find that it is a +5, so we can say in case of acid and base, there is a formation of a oxo anion and oxo cation, it is there. So this is very important reaction which is given in the NCERT. Here some points we can select from the NCERT, that is for the CO2 plus N, CO2 plus, that not CO2 plus, yes, Cu plus 1, it can disproportionate, in the, so Cu2 Cu plus 1, it can disproportionate into Cu2 plus and Cu. Since we know it is a Cu2 plus is a more stable than the Cu, so it will get disproportionated in the aqueous medium. Okay, so this is very important. So since it is a compound of a copper 2 plus, copper 1 plus, it is unstable in a aqueous solution, so it will undergo the disproportionation reaction like this. Okay, next it is a copper 2 plus of a halides. Copper 2 highlights it as a copper 2 plus highlights means that we can say it as a CuX2. CuX2, it exists like this. Cu, for this we can say it is a Cu Cl2 exist, Cu Br2 exist, but Cu I2 does not exist. Does not exist. What is the reason behind that it does not exist? Basically, it forms a what? X minus, I minus, basically I minus, it gets converted into iodine. So that's why it is a very good reducing agent. Very good reducing agent. This will reduce a Cu2 plus Cu2 plus 2 Cu plus 1. So this will occur in the case of a CuI2. That's why it does not exist. Next, the stability of a Cu2 plus rather than the Cu plus aqueous is due to the much higher negative of a hydration energy. It is a very negative, and which is more than the compensate for the second ionization enthalpy of a copper. The ability of oxygen to stabilize the higher oxidation states is demonstrated in the oxides. That highest oxidation number in the oxides, it is a coincide with the what, the group number only, and it is attained in the scandium 2 manganese 2, and amine, it exists as a what, that we can say Mn2O7. Beyond the 7 group, it is a no higher oxidation state of a Fe. It is only this, it does exist known, although ferrate it is there, forms in an alkaline medium, but rarely decomposes to the Fe3 plus and oxygen. Beside the oxides, oxocation, it is there, that we have seen. This is the main thing we have to remember in case of oxides. Okay. Next, we can see the some compounds of a D block element, which is very, very important. The important one, that is a potassium dichromate. So potassium dichromate, it is made by the chromite ore. When chromite ore, it is heated with the sodium chromite, sodium that it is a give. We can say it is a sodium it is a Na2CO3. It is given with the oxygen. In presence of oxygen, when it is heated, then heated means roasted. Roasting means it is a ore roasting. It is occurs in the presence of air. Then it is a formation of sodium, this Na2CrO4. When it is acidified, that will be converted into sodium dichromate, that is a Na2Cr2O7, and this it is heated with a KCl, and it will be converted into K2Cr2O7. So this is a formation of K2Cr2O7. So what is a keynote? It is a very important, and K2Cr2O7, it is a preferred over the Na2Cr2O7 as it is a primary standard in the volumetric estimation. Why it is so? Because of Na2Cr2O7 is a hygroscopic, which absorb water, and that's why it is used this one, that is a K2Cr2O7, not Na2. This salt, it is a hygroscopic. Next, the properties of this compound. Some physical property, it is a orange red colored crystalline, it is there, okay, which it is moderately soluble in the cold water but freely soluble in the hot water, and it melts at a 398 degrees Celsius. And the chemically, if we see it as in case of a basic medium, it will get converted into the yellow compound, that is a chromate, it is there. So chromate and dichromate can be interconverted into the acidic medium and basic medium. Basically, it is a orange color can be changed into yellow color if basic medium it is there. If acidic medium it is there, we can say it is getting converted into the orange from yellow. Okay. Effect of a heating, it is also very important. It was asked many times. So when we heat potassium dichromate, it will get converted into the potassium chromate and chromium oxide with oxygen. So one salt, oxide, and oxygen. Salt, oxide, oxygen will be formed. Okay, this is a heating effect of a sodium dichromate, potassium dichromate basically. So next it is a chemical properties, that is a, this is alcohol, C2H5OH. So basically this is a also oxidizing agent. This is a also oxidizing agent in acidic medium. In a acidic medium, it will get converted into Cr3 plus, which is a green in color. Cr3 plus. So basically, whenever the oxidation occurs, that is a conversion of a +6 to +3. It is occur from +6 to +3. It is a from color change. It is there. That is a from orange to green. From orange to green. So in case of SO2 gas will be converted into sulfate. Sulfide will be converted into sulfur, and sulfite it will be converted into sulfate. NO2 it is a converted into NO3 minus. So NO2 minus it will converted into NO3 minus. Iodide will be converted into fluorine, bromine, bromide, bromine. Fluoride cannot be converted into fluorine. This cannot be possible by that oxidizing agent. Next it is a thiosulfate will be converted into sulfur and sulfate. Alcohol will be converted into acid. SN2, SN4, Fe2 plus, Fe3 plus. That only you can remember. This is a reactant. This is all. It is a given. That is a reactant, and the tails of all the reaction it is given. That is a product we are getting. Okay. Question it is a given. Which of the following statement? Which of the following statement it is a? Okay. Which of the following statement is a correct when SO2 it is a passed through acidified K2 Cr2O7 solution, it is a given. Okay, so potassium dichromate it is a given. So when SO2 is passed through this, then it will be getting converted into SO4 2 minus. Basically it will be converted into sulfate. Either also it is also we can say it as a SO3. So SO2 it is a getting reduced, that is a incorrect. Green color of Cr2 SO4 3 it is formed, that is a green color of a compound will be formed, that is a Cr3 plus with a SO4 it will form what? Cr2 SO4 whole thrice. So Cr3 plus will be formed, that is a correct, and it is a green color. The solution is a turns blue, that is a wrong. It is getting converted into green color. The solution is a decolorized. No, it is a not decolorized. It is a getting converted into green color. So our option is a correct. That is a B option is a correct. Next, it is a potassium permanganate. It is the formation of a potassium permanganate. It is a with in the presence of air when it is a KOH. It is a heated with the KOH. It is a heated. Then it is a formation of a potassium magnate, and potassium magnate in acidic medium it gets converted into the potassium permanganate, and along with that we will get that is the MnO2 and water. So this is a formation of potassium permanganate, and other option it is also there, that is a MnO2. It is a when it is a heated with this potassium carbonate, it is a with oxygen it gives a what, that is a potassium permanganate. Okay, so basically it is a potassium permanganate which is a green in color getting converted into potassium permanganate which is a purple color. So purple color it is a crystalline. In case of a crystalline it is a soil. If I take it as a solid form, in solid form it looks a black color, dark black. In solid state it looks a dark black, but in case of a solution we can say it as a purple color will be formed. and it has a properties that we can say. First physical property, it is a purple color crystalline compound. It is a moderately soluble in the water at a room temperature. The magnet and permanganate ions are what? It is a tetrahedral. So if you say it is a permanganate, it is a given. So if I take a permanganate and magnet, that is a K2MnO4 and KMnO4. So KMnO4, it is a what? MnO4. If I make ions, that is a MnO4 minus. So MnO4, it is a having a 4 oxygen with 3 oxygen, it is a double bonded, 1 oxygen, it is a having a negative charge, and resonance will be there, that we can say here it is a sigma, it is there sp3. 4 sigmas are there, that we can say it is sp3, and it is a tetrahedral. And this is also diamagnetic. Color, we know it is only due to the, so color, it is what? Due to the, due to color is due to, so color of a compound is due to what? Color of a compound, color of this compound is due to charge transfer. So basically charge transfer occurs, and due to that we get a what? Color. So this is the properties. Next, it is a K2MnO4, that is a 2 oxygen will get a what? Negative charge, that is a 1 oxygen, 2 oxygen, and these are the cases where it is this one, it is a potassium magnet, which is also a tetrahedral. Second, it is a sp3. Third, we can say it is having a 1 electron free, which is making it as a paramagnetic. As we know, the 7 electrons are there. Out of 7 electrons, only 6 electrons are used, so 1 electron will be free, that we can say it as a paramagnetic nature will be there. So in case of both compound, that's potassium dichromate and chromate, these are the properties. And this, it is a heating effect of potassium permanganate. Heating effect of this, it is when it is a heated at a 513 Kelvin, it is a converted into the potassium magnate and the manganese oxide with the this oxygen. Again, it is a formation of a salt, either it is a oxide, and oxygen will be formed. Potassium permanganate, it is a powerful oxidizing agent in a alkaline medium. KMnO4 solution is also known as a Bayer's reagent, which is having a 1% alkaline KMnO4 solution. It is a very important. Now it is a, this part we can see it is a, in next slide we can see it as a KMnO4. It is a strong oxidizing agent also. So KMnO4 in acidic medium. So KMnO4 in a acidic medium. It get converted into the Mn2 plus, and KMnO4 in a neutral or a alkaline medium. Neutral or alkaline medium, it get converted into the Mn4 plus, and in case of a basic medium, it gets converted into the Mn6 plus. And that is very, very important to do the redox questions also. MnO4 minus, it get converted into Mn2 plus in the acidic medium, and the conversion of this reagent, like we can say oxalate will be converted into carbon dioxide, sulfur dioxide will be converted into sulfate, sulfide will be converted into sulfur, the Uh, Thiosulfate will be converted into the sulfate and sulfur. Nitrite will be converted to nitrate. So this all will be converted, but fluoride again it will be not converted into fluorine. Reason is the same. Fluorine is a very strong oxidizing agent than the KMnO4. So as alcohol will be converted into acid, Fe2 plus, Fe3 plus, Sn2 plus, Sn4 plus. Okay, so these are the conversions of in case of KMnO4. Next, we can see the some question, that is a name the gas which is a that contain that can readily decolorize the acidified KMnO4 solution. First of all, those which can be oxidized, those compounds which can be oxidized are used to decolorize the KMnO4. Since KMnO4 it is a given, that is a what, KMnO4 it is a purple in color, so it will convert it into the Mn2 plus, which is a colorless, okay. So let's see which option it is a given. So 4 plus it is a given. So 4 SO2 can be converted into SO3, that is a SO, that is a change. We can say it is a 6 plus is there. NO2 it is a having a 4 plus, it is not a maximum. P2O5 it is a plus 5. Carbon dioxide it is a plus 4. So we can say it is cannot be oxidized. Oxidation cannot be occur. Here also oxidation cannot be occur. That there is the two cases where oxidation can be possible. But here we can say, here it is a 4 plus 2, 5 plus it is a NO3 minus, and here it is a 4 plus 2, 2 plus, 4 plus 2, 6 plus it is there. So which it is a getting it readily converted, that is a easily it is a converted for the what, SO2 will be easily converted to the SO3, as it is a in case of nitrogen it is a 4 plus 2, 5 plus it is a converted. Okay. So SO2 it will decolorize the KMnO4. Bayer's reagent, what is the Bayer's reagent? It is a alkaline solution of a KMnO4, it is a 1%. So 1%, if it is not given, we can say cold diluted aqueous solution of a potassium permanganate, it is also a Bayer reagent, we can say it is a Bayer's reagent. Next, it is a identify the incorrect statement. First statement, it is a given. The transition metals and their compounds are known for their catalytic activity due to their ability to adopt a multiple oxidation state and to form a complexes. That is the correct. So it can form a complex and it has a variable oxidation state. That is a true. Next, it is a industrial compounds are those compounds which is formed when the small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of a metal. That is a true. The oxidation state of a chromium, it is a given, this or not same. So if find the oxidation state of a chromium, that is a it will come, that is a +6 and +6. So which is a same here. We can say this is a false statement, it is a given. Next, it is a chromium 2 plus D4, it is a stronger or reducing agent than the Fe2 plus in a water. So as per the SRP value, we can say this is the correct answer. So the C option is it is a our incorrect option, it is a given. Next, which of the following ions exhibit a DD transition and the paramagnetism as well? So for this we can see it is a DD transition will occur or not. First of all, that if we see the configuration of it is a chromium 6 plus. So chromium 6 plus it is a D0. In case of this, it is also chromium 6. We can say here it is a D0. Mn, it is a in case of this, it is Mn6 7 plus, it is a D0. MnO4 2 minus. So in case of MnO4 2 minus, it is a +6. In case of a plus 6, it is a D1 will be there. So we can, there is only one possibility where it is a paramagnetism is a possible, and if it is an unpaired electron it is there, we can say there is a possibility of a dd transition is also there. In all other options we can say it is a d0, it cannot give any paramagnetism. Next it is a inner transition element. Inner transition elements, that is a F block. F block, it is a classified as a 4F series and the 5F series. When the last electron enters in the F orbitals, this is known as a what? Inner transition elements. So this can be classified into, that is a lanthanides and actinides. So what are the lanthanides? Lanthanides are those elements in which last electron goes in the F orbitals. So general electronic configuration, it is this 4F1 to 14, D 0 to 1, it is a 6S, it is a 0. So in this case we can 6S, it is a 2. In this case we can say lanthanides configuration, it is a given. In all the configuration it is the same. The differences where it is we can say D, it is a F, it is a 0. F, it is a 0. Cerium, it is also have a, that we can say first of all the we have a 54 for the xenon. So after xenon we are filling this, that is a 4F, 5D and 6-2. So to fill this we can say 6 as will always get a 2, as will always get a what? 2 electrons. So it is a 54 electrons here we have filled in case of a xenon. So 54 after it is a 2 electrons here, it is a we have filled. Next it is a, for example we are doing the configuration of a cerium. So cerium, it is a there. So for cerium it is a atomic number, it is about 58. So 58 electrons we have to fill in the orbitals like this. So it is a 57, so 56 we have filled. 2 more electron we need to fill. So those 2 electrons will be filled in the what? It is a 4F1, it is there, and D1, it is a 1. In case of a D, it can be 0 or 1. So that we have to remember, where it is a 0 and where it is a 1. So in case of all this, it is a cerium, it is a 1, where it is a D, it is a getting 1. In case of gallium, it is a D, it is a getting 1. Otherwise it is a last one, lutetium, it is a getting D1 configuration. Otherwise in all the cases it is a getting D0 configuration. So generally you can remember that is a star 1, it is a getting D1 configuration. Otherwise it is a D0. All the star 1s, it is a getting what? D1 configuration. Okay, after the filling the D electrons, it is we can fill in the last electron in this F orbital, and this can be followed for a lanthanide and actinide as well. And why does the variation of electronic configuration that we can see here? It is the orbitals, it is having a very similar energy, and they have a similar energy, then we can say electron can be transferred from the one orbital to another orbital to get a more stability. So what is the exception? It is there, exception is there. So what is the reason? First, it is a half filled. Half filled means the one orbital, it is a D7. Fully filled, that is a F14. Another thing is a small energy difference. Small energy difference. So these are the 3 reasons. That's why it is a configuration. It is not always regular. So these 3 elements we can remember. That is in case of a lanthanum also it is there, D1. So lanthanum, it is there, cerium, it is there, and gallium and lutetium, it is having a different configuration than the regular one. So what is the regular one? We can, so it is first we fill in the 6 s orbital, then we fill in the D according to the given table. We have 4 elements where it is a D1, it is a getting. Otherwise we can fill all the remaining electrons in the f orbital. This is a way to do the configuration of lanthanides. So what are the properties? So first it is a size of size, it is increases as we, so top to bottom. First of all, we can say that left to right, across the period, as we move from left to right, as we move left to right, the size, it is decreases. Reason is what? That is a lengthenide contraction. Either we can say here it is a d orbitals, sorry, f orbital, 4f electron it is there, 4f electron it is there, that's why it is a contraction it is there. And in case of ionic and atomic size, it is a regular variation is there, there is no exception. As we move left to right, the size, it is a decreases. Okay, next some properties that is like this. So physical properties, they have a silvery white, it is a soft metals, turns rapidly in the uh, air. Typically metallic structure, it is a good conductor of a heat, good conductor of electricity. Oxidation states of a lanthanide, it is a mainly in case of a, mainly it is an exist in the +3, it is a stable oxidation state. +3, it is a stable oxidation state of a lanthanum. And some compounds of a lanthanum we can form with the lanthanides will form with oxygen, it will form what? It is a Ln2O3. With sulfur it will form Ln2S3. With nitrogen it will form Ln. So that we know the formula formation, it is what? Ln, since it is having a +3, and sulfide it is a what? 2 minus. Then we can do cross multiplication of their oxidation state. There is a formation of a formula that is known as a compound of this. We can say it as a this. No, this is not oxide. This is a sulfide. So Ln2 and S3. So this is a way to form what? Compounds of lanthanums. Carbide it is there. Hydroxide it is there. So with water it gives a gaseous substance, that is a hydrogen. And with what? Acid also it gives a hydrogen gas. And salt, it is a always form. Salt formation is there. With halogen it is a LNX3. LNX3, it is a type of a compound will be formed. Next we can say there is a question we can do. Which of the following state of ions act as a oxidizing agent? As we know, the lanthanum, it is a more stable in the +3. So if it is a higher oxidation state, it is there. For example, this. If it is a cerium, it is a 4+1, 4 plus it is a given. It will get converted into +3. So +3 it is a getting converted. That means reduction is a happening. For the spaces, it is a happening reduction. Then it can say it is a oxidizing agent. Similarly, we can say Tb4 plus, it is also oxidizing agent. So first option it is a correct, as it is not in the 3 plus. This, as it is a given in 2 plus. So U2 plus it is a given. So U2 plus in this case it is a, if it is a Ln2 plus it is a given. Ln2 plus it is a given. So it will get converted into Ln3 plus. For any lanthanide, if it is in the 2 oxidation state, it will get converted into 3 plus. So since this is a oxidation, so the species itself is known as what? It is a reducing agent. Next is a actinides. In case of actinides, it is a 5F 1 to 14. Next it is a 4. This is a 5F. Next it is a 6D and 7S. S it is a 2. D it is a, it may be 0 or 1. So this is a general electronic configuration of actinides. We can say in case of this D1 it is a getting for the actinides, it is a getting D1 configuration. Otherwise normally it is a D0. Normally it is a what? Normally it is a D0. In some cases, it is a D1 configuration. It gets that is a actinides. D1 it is there. That is a protactinium, uranium, neptunium, curium. The last one that is a lawrencium. In these all cases, we have a D1 configuration. Otherwise, a D0 configuration. We can feel the electrons like electron filling. Electron filling we can do. That is a first we fill in the what s orbital. Then we fill in the d orbitals depending on the 0 or 1. For 1 we have to remember the star marks the element, and then we can fill the remaining electron in the f orbitals. That is the way to the for a electronic configuration. Next it is a properties. It is a normal that we can say if we go left to right, density will increase. Melting point it is a, and boiling point it is also increases. And electropositive character it is a very important. As we move left to right, either we can say it is a from top to bottom. First of all, we can say from top to bottom it is a, in case of actinide or lanthanide, top to bottom metallic character it is a increases. Metallic character it is a increases. So if metallic character it is a increases, we can say its electropositive nature will also increase. Due to the poor shielding of a 5f orbitals, actinide contraction is more effective than lanthanide contraction. Okay, this is also important. Actinide contraction is a more effective than the lanthanide contraction. Okay, next it is a question we can see, that is a this. So choose the correct answer from the options given below. Lanthanide elements we have to select, that is a lanthanide element, that is a cerium. D block elements, that is a Mn. P block element, that is a arsenic. S block is it is a cesium, that we can say lanthanum. It is a, this is also from the PYQ question. So PYQ it is also like this, the element and block it is a given. So first it is a first, second it is a D, it is a 4, B it is a 4, third it is a C, it is a, we are getting second. So our C option is a correct. The reason for the greater range of oxidation states in the actinides, it is attributed due to what? So as we know, it is also shows what actinides. In case of actinides, it also shows oxidation states of actinides. It shows a +3. Along with that, it can shows a +2, +4, +5, +6. Okay, this oxidation states is also there in case of actinide. Lanthanum, mostly it shows in oxidation state, that is a +2. So what is the reason for that? We can say it is a actinide contraction. It is there. 5f 6d 7s levels are having a comparable energy. 5f and df 5d it is levels being a close energy. The radioactive nature of actinides, so that we can say it is having a comparable energy. Okay, so that is also a reason for the having a variable oxidation states in case of actinides. Next we can start, that is a coordination compounds. So what is a coordination compounds? Okay, so coordination compounds, basically it is also a characteristic property of D block elements. So mainly D block element forms of what? The coordination complexes. Basically it is a compound which is containing the coordinate bond typically between the central metal atom and ions and the number of other atom or groups are there. So we can say here coordination compounds is basically formed by the one central metal atom, it is there. Central metal atom, it is there. And this is having a vacant orbital. Since metal, it is metals of d block, it is having a vacant orbital, it is also there. And some species are having lone pair. The species which is having a lone pair, which is known as a ligand also, which is known as a ligands. Basically what it does, the lone pairs of ligand is shared between the metal and ligand. It is shared between the metal and ligand, and this is all also known as a coordinate bond. This is known as a what? Coordinate bond. So the complex which is formed by the coordinate bonds is known as the complex compound. So it can be a more than one ligand, it is there, as a more than one vacant orbital, it is possible in case of a metal. So it can form what? Metal complex. Okay, now let's see different terms about the coordination compounds. So first of all, the coordination compound, it is a first theory, it is given by the Werner about the coordination compounds and their identification, which is done by that Werner. One experiment he does and concluded there is a two type of valencies. First valence is primary valency, which is known as a ionizable valency. For example, K4 Fe Cn whole 6. It is a given this. So for this we can say in case of this ionizable ion, it is always written outside that square bracket. This is known as ionizable, and this square bracket term, it is known as non-ionizable. Non-ionizable. Okay, so basically it can be converted into what? 4k plus and Fe Cn whole 6 4 minus. So this it is given by primary valence. It is what? It gives ionizable ions. Secondary valency, it is about a non-ionizable ion. So the secondary valency of and primary valency of this complex, if I say it is a F, it is coordinated with the 6 cyanide. With the 6 cyanide, it is there. And other ions which is connected, that is potassium plus. Potassium plus. Okay, so this is our complex where it is a primary valency and secondary valency. We can say here primary valency, it is known as it represented by the dotted line, and so we can say it is represented by dotted line. And this is represented by solid line. Primary valency, it represents the oxidation state. Oxidation state of a metal. Central metal atom is known as a water. Primary valency. The secondary valency, it is for the what? It is a coordination number of. So what is the coordination number? Later we will see. So coordination number of central coordination number of complex is known as a what? That secondary valency. Next, it is the experiment which gives the result, that is like this one. So Werner does the experiment, that is COCl3 with 6 NH3 on reaction with the AgNO3. It gives 3 moles of AgCl. That means the 3 ions are free from the chloride, it is a cobalt. NH3, that is a 6. So 3Cl it is a there. 3Cl it is a there. So that means it can give a, if it is a giving 3, if it is a giving 3 moles of 3 moles of AgCl, that means the complex will be like this, where 3 ions can be ionized. Next, if it is a 2 moles of AgCl it is given, that means it is a 2 chloride, 2 chlorine will be there. The complex structure will be what? That is a cobalt, NH3 ammonia it is there, and it is a 5, and 1 chlorine will be there. So 2 moles we are getting, that means 2 chlorine will be outside, 1 it is inside. Similarly, for this we can say we are getting only 1 mole of AgCl, that means 1 Cl will be outside, other will be inside. That means 2 Cl it is inside, 1 Cl it is outside. The remaining will be, it is ammonia it is there, which is working as a ligand. Now it is also there, as the number of ions it is increases, number of ions it is increases, its electrical conductivity will also increases. Electrical conductivity will also increase. As we know, the number of ions, more will be the electrical conductivity. So this is also the conclusion of our experiment, that we can find the structure of that complex if we do the this reactions. Now let's see the coordination compound, which is we know it is uh, any salt. For example, first of all, let's see, any salt, it can be divided into two part, it can be classified into two part. That is one which is known as a double salt, and other salt it is known as a, if we mix one or more than two salt, if we mix more than two salt, they can either form double salt, either they can form what? Coordination salt. If it is a forming a double salt, then it means we can get ions of all the, so the salt can be broken into their ions. But in case of a complex ion, it is not possible. In case of a coordination compound, it is only ionizable part will be ionized, form ion, otherwise it is remain in the solution, and the complex which is not ionized, that is known as a complex sphere, that is also known as a complex sphere. So if it is a giving uh, all the taste of ions, then it is a double salt. If it is not giving the all the ions taste for the all the ions, then we can say it is a coordination complex. Next is a homoleptic and heteroleptic. So what is a homoleptic and heteroleptic? So homoleptic, it is a homoleptic if it is all the ligands, all ligands, if all ligands are same, then it is a homoleptic. And another term, it is a heteroleptic. So what is a heteroleptic complex? Heteroleptic complex are those complex where all ligands are not same. Okay, so for example, it is a homoleptic if it is there. If it is a homoleptic, it is there. Then, for example, NiCO whole 4. This is a homoleptic. This is a homoleptic. Heteroleptic, for example, it is a CO NS3 whole 4 Cl2 Cl. So this is a heteroleptic, as a two type of a ligands is there. Two types of a ligand. One, it is a ammonia, and other one, it is a chlorido. So this is it. That's why it is a one. It is a different type. Two types of a ligand it is there. Then it is known as a heteroleptic complex. Okay. So this question, it is asking about a homoleptic complex from the following. options. First question, it is given that is a diamine chlorido. So two amine is there, one chloride is there. So that means it is a two types of chloride is there. Then it is not a homolaptic. Pentaamine, pentaamine and carbonate. It is a so it is a pentaamine. So different type of ligand is there. It is also not a homolaptic. Next, it is a triamine, triamine, triaqua chromium. This is also not a homolaptic compound. Next, it is a potassium trioxalato aluminate. This it is only we have a one type of a ligand, that is a oxalate. That means that this is a homolaptic complex. Next question, it is which of the following forms a set of a complex and a double salt respectively? So that we can say, first of all, the double salt can be formed by any type of metals, but the complex it is mainly formed by the D block elements. So first it is a given that is a CuSO4 5H2O, that can form a what? It is a it can form complex. This also can form a complex. So this is our not a correct option. Next, it is a this one platinum can form a complex. This can also form a complex. This is not our answer. Next, it is a this one. This platinum can form a complex, and Kl it is a given KAI is a complex would be Ka K2SO4 K2SO4 Al2SO4 whole twice. So this complex it is a given. So it is a typo error. So this it is a salt, which is we know it is a double salt, and this can form a complex. So our C option is a correct. And the next it is a given that is a nickel and nickel, which can form a what complex. Next it is a some basic terminology about the coordination compound. So coordination compound it is having a one central metal atom. So what is a central metal atom? So the metal atom which is accepting its lone pair from the ligands. So what is the ligands? Ligand it is having donating its lone pair to central metal atom, and this is accepting it's a central metal atom. And this central metal atom it is accepting lone pair. We can say it is a Lewis acid. It is also known as a Lewis acid. Since it is giving its lone pair, we can say it is a Lewis base. Here it is a coordination number. What is a coordination number? Basically it is a total number of coordinate bond. Total number of a coordinate bond. It is formed with a central metal atom, and it can be finded by using the formula, that is a number of ligands into its density, that we can find the number of a total number of a coordinate bond. Next, it is the ionization sphere. The outside ion it is known as the ionization sphere. The inside this it is a this whole it is known as a coordination sphere, complex sphere. This it is a non-ionizable. This is the basic terms of a coordination compound. Next is a ligands. What is a ligands? So ligands are the species which have a lone pair and can donate to the central metal atom. On the basis of a number of electron pair available for the donating, ligands can be classified as a ligands. First of all, it can be classified on the basis of a charge, that is it can be neutral and anionic or cationic. and it can be further classified as a dent on basis of a denticity. Denticity, it is a what? It is a number of a coordinate bond. It is a number of a coordinate bond can form. So if any species can form a one coordinate bond, then we can say it is a monodentate. If it is a two coordinate bond can form, it can be known as a bidentate. Polydentate, it is a more than one, more than two. Flexidentate, if it is a any ligands can have a flexible denticity. So let's see one by one. First of all, it is a neutral monodentate ligand. Neutral monodentate ligand, it is a named, it is a only as a species name. For example, it is a NS3. NS3, it is a named as a amine. So ammonia, it is not, it is a ammonia. Name of a ligand will be what? Amine. H2O, it is a known as a aqua. NO, it is known as a nitrosyl. PH3, it is known as a phosphine. It is known as PS3, it is a triphenyl phosphine. Oxygen, it is a dioxygen. Nitrogen, N2 gas, it is known as a dinitrogen. Since it is all having a lone pair electrons, they are named like this one. And next, it is a anionic monodentate ligand. So anionic monodentate ligands are named as a name of a anionic monodentate ligand. It is a first we remove what? Remove E at end and add O at end. So first remove what? E later and then add O later at the end of a name of a ligand. For example, it is a name of a that ion. First we are checking for the name of ion. It is about the name of ion. It is what? Fluoride. This is a fluoride ion. So if we remove a E later, it is a fluoride, and it is a removal of A and addition of O. It will form what? Fluorido. Fluorido or fluoro, it is the same. Chloride. Similarly, we can say chlorido, chloro, bromido, bromo, iodido, iodo. Okay, so this is the name of highlights. Oxide, it is this. Sulf oxide, it is this. Then we can say it is a oxido. Sulfide, it is a sulfido. Similarly, this name of ligand, it is there. In case of name of cationic ligand, it is a the suffix we add, that is a suffix we add, it is a I U M. IUM we add in the case of a cationic ligand. This is a oxide. From oxygen, it is a form. This is known as a oxysium, oxygenium. It is a nitrocelium. This is a nitronium. What is a hydrogenium? It is a NS2, NS2 plus. So this is known as a hydrazonium. This is a hydrazine. This is a hydrazine. If we add a one, this is NS3 plus. Okay, so if it is this one, we can say it is a cationic ligand. This can donate its electron pair. So this is a cation, naming of a cationic ligand. These all are the monodentate. Next, it is a bidentate and tridentate. Okay, next it is a bidentate ligand. So bidentate ligand, it is a ethylene diamine. Ethylene diamine, it is a what? It is a having a two nitrogen which can donate electrons. So these are the list of ligands which it is a given the denticity of a ligand. It should be remembered. All the ligands you should remember with their denticity. So this is also important. That is a EDTA. EDTA, it is a ethylene diamine tetraacetate, and it is a having a denticity. It is a 6. Denticity, it is a what? Denticity of this ligand is a 6. It is a hexadentate. Tridentate means Tridentate, it can form a three uh, number of coordinate bonds. Now it is a formation of a ring. We can find the number of ring it is a formed, that is equal to the denticity minus 1. So if denticity it is a 3, we can say the number of ring it is a 2 ring will be formed. In case of tri this tetradentate, it is there, denticity it is a 4. For the 4 denticity we can have a 3 rings, that we can say it is a 3 ring it is a formed. So these are the point you should remember for the ligands. Next it is a type of a ligand, it is a, that is a ambidentate ligand. Ambidentate ligands are those ligands which have a more than, which have more than one, more than one donor, more than one donor atom. For example, more than one donor atom, but at a one time only one atom can donate. For example, it is a cyanide, it is a given. So it can be donated from the carbon, as well as it can be donated with the nitrogen also. If it is donated from the nitrogen, we can say it is a isocyanide. It is a cyanide, this is a isocyanide. Similarly, more examples are there, like it is a cyanato, that is a, either we can take that is nitro, that is NO2, ONO. Okay, these are the ligands which can be ambidentate. Next, it is a flexidentate. Flexidentate means it is a flexible, that we can say variable denticity. Variable density means the density can be changed for the species. For example, the SO4 2 minus can have a density, it is a having a 2 or a 1 depending on the given complex. In this complex, we can say SO4 2 minus act as a what, monodentate, since it is a donated by the one atom, oxygen atom. If it is a donated from the both oxygen atom, then we can say this is a bidentate. So the sulfate itself, it can work as a what, monodentate as well as a bidentate. So if a same ligand, it can work as a bidentate, monodentate. If denticity it is a different for the different complex, then we can say it is a flexidentate ligand. So this is a question, it is a given. Which of the following is not an ambidentate ligand? Ambidentate ligand means those ligand which can have a more than one donor atom. So first, if I say it is a oxalate, in case of oxalate, it is a only one donor atom, it is there, that is oxygen. So this, it is thiocyanide, it is there. So in case of a thiocyanide, it can be donated from the nitrogen. It is a nitro. This is a so nitrogen and sulfur, it can be donated from the both way. Then we can say it is a thiocyanide and a cyanide. So cyanide, it is there, and it is a it is a isocyanato. Isocyanato, it is also our ambidentate. This is also ambidentate. This is also ambidentate. This is not a ambidentate, as it is only one type of atom it is there, that is oxygen. So the species must have a what, more than one type of atoms to donate its lone pair. Okay, next question, it is next type of a ligand it is there, that is non-classical ligands. Classical ligands are those which can form a what, normal type of bond, that is a coordinate bond. So they non-classical ligands are what, those ligands which form a what, basically we can classify the non-classical ligands as well, that is first, it is a sigma donor and pi acceptor. Sigma donor and pi acceptor. And other type of a ligand, that is sigma donor, sorry, pi donor, it is there, and pi acceptor, pi donor and pi acceptor. So those ligands which donate its sigma electron, for example carbonyl, so carbonyl, it donates its electron pair, that is to the metal and its vacant orbital. So carbon, it donates its electron pair to the metal, and metal, its metal donate its lone pair to carbonyl anti-bonding molecular orbital. So this is a pi anti-bonding molecular orbital. This is known as a sigma donor and pi acceptor. Since it is a sigma, this is a pi. So by the pi bond, it is accepting the electron, and this is also known as a special type of a bond, that is known as a synergic bonding. This is known as a synergic type of bonding. In case of a synergic bonding, the bond order of a CO, if I say it is a more the synergic bonding, it is a, if it is a more synergic bonding occurs due to more synergic bonding, due to more synergic bonding, what will happen? First, between the carbon and oxygen, bond order basically decreases, and between the metal and carbon, bond order, it is increases. This is very very important. Next, it is a type of a ligand, it is a pi donor and pi acceptor. In case of this, ligands like benzene, so benzene, it is there, which is having a pi electron density, so it can be donated to the chromium, for example this, it is a given. So chromium can take its electron pair, and it can give its electron pair to the ABMO. So that is also a type of a pi donor and pi acceptor, since it is donating its pi electron and accepting its a pi in its pi anti-bonding molecular orbital. So these complexes are example of a, so this is also known as a sandwich complex, and this is a ferrocene, which is very important. It is also known as a sandwich complex, in which it is a, this, it is there, complex is formed by this Fe with cyclopentan, cyclopentan, pentanyl, it is there, and this is a two ligands are there. So this is known as a ferrocene. Next thing, it is rules for naming of coordination compounds. So basically, we know the naming, it is done for the first, it is any salt, it is a given salt. For the any salt, we name first cation, then anion. That is the first rule we know. That is the first rule. First name the cation and then anion. So in the naming of a coordination sphere, ligands are named first in the alphabetical order, followed by the metal atom, and then oxidation state of a metal, it is written in the parenthesis in the Roman numeral. The prefixes like ditritetrates are used for the when it is a more number of a ligand, it is a coming more than one ligand, it is a coming. If the ligand name, it is included in such like, and the if ligands, it is a containing the name like ditritetra, then we can use that base for the two ligands, tris for the two ligands, and then it is a, for example this compound, it is a given. First of all, it is a cation, it is this one, anion, it is this one. So in case of this, we can write the cation name, it is a first. So first, it is a name of a ligand, that is a triaqua. So name of a ligand, it is a aqua. Here it is the name of a ligand, it is a amine. So I can say amine, it is a coming first. So it is a tri amine, tri, I mean tri aqua. Then it is a chromium. And the complex, it is a having oxidation state, that is a, we can find that is a +1, it is there. So one chromium it is there. So this is a name of a coordination compound, and mostly name of a compound you can compare with the options also. So that is not that much important for the naming. The naming of a compound, complex compound like a brazing ligands. If brazing ligand it is there, then we can use a prefix that is a mu. So mu it is added before the name of a ligand. If it is a ligand, it is coming on the breeze. So this complex, it is written like this. That is a bis di bis. It is a ethylene diamine. Cobalt it is there. Cobalt it is a oxidation state. It is a 3. It is there, and for this also it is a 3. And next it is a mu amido, it is there. This one amide it is there. So amide it is on the breeze, we can add, that is a mu. So again it is a breezing ligand, it is there, that is a hydroxo. So hydroxo, mu hydroxo, it is a bis, that is a ethylene diamine, cobalt 3. Next last one, it is a sulfate, it is there. So this is the name of a complex we can do. The last part of this, it is not last part, the isomerism it is there. The next we can see it as a bonding in the coordination compound. So let's see first of all the isomerism. So isomerism can be divided into two parts, that is a structural isomerism and stereoisomerism. So what is a structural isomerism? Structural isomerism are those isomerism which is having a different connectivity of a bond, and the bond, it can be a primary valency, it can be secondary valency. If bonding connectivity it is a different, then we can say it is a structural isomerism. So first, it is a structural isomerism can be divided into four type of ligands are there. Four types of isomerism is there. That is a ionization isomerism. If the same molecular formula but having a different ions in solution. For example, this complex it is a given. So if it is a dissolved in the water, then it will give a SO4 2 minus ion, and the other it is a complex which is a given. It will give. In case of this, if we dissolve in the aqueous water, it is a, if we dissolve in water, it will give a ion that is a bromide. Now we can say it is a both complex. It is a having a same number of same molecular formula, but it is a having a different ions, that is a sulfate and bromide. So we can say this is a having a different ion. So this complex are known as a ionization isomer. Next type of isomer it is a, that is a hydrate isomerism. So this is a isomerism which is a having a same complexes which is having a same molecular formula but different number of water molecules associated with a central metal. For example, it is a CrH2O whole 6, it is a Cl3, has a 3 possible hydrate. It is a hydrate isomer. It can be possible, like if it is a 6 hydrate, it is a coming inside, then we can say 3 it is a coming chloride, it is a coming outside. So it can be exchanged, means it is a hydrate, number of hydrate it can be different. So it is a working as a monodentate ligand. Okay, so chromium it is in the +6. Chromium it is a forming a coordinate bond, that is a 6. That means the coordination number it is a 6. So it is a 5 1. Here it is a 4 and 4 by using the hydrate and chlorine it is a forming a 2 bonds. That means it is a having a different number of water with a central metal atom, So if it is a different number of a hydrate water molecule it is there, then we can say it is a hydrate isomer it is there. Next is a linkage isomers. What is a linkage isomerism? Those isomerism which is a having a ambidentate ligand. If it is a having a ambidentate ligand, we can say linkage can be different. For example, it is a NO2. NO2, in case of this NO2, or either it can be attached with the nitrogen, either it can be attached with the oxygen. If it is attached with the nitrogen, connectivity will be different. Oxygen connectivity, it is a different connectivity. Basically, it is a different. Then we can say it is a different linkage isomerism we can get. The last one, it is a coordination isomerism. What is a coordination isomerism? Those isomers which have a same molecular formula but having a isomer having a both anion and cation as a complex. Basically, this is a poly sphere, it is there. Poly coordination sphere, it is there. And can inter exchange of ligands is a possible between the metal. So there is a exchange of ligands from one coordination sphere to the another coordination sphere. So if it is a forming this way, we can say that this is known as a coordination sphere. So to find the total number of a coordination sphere, we can use the formula just to remember this one. For example, there it is a given here. So what is the condition to find this, to use this formula? So to find the total number of a coordination sphere, that we can use, if the same if the same central metal atom it is a given and same coordination number it is a given, and monodentate ligand should be there. If monodentate ligand it is there and coordination number it is the same, then we can say if it is a central metal atom it is the same. If central metal atom it is the same, then we can use the coordination number of a complex divided by 2. For example, this it is a given. For this, we know it is a central metal atom. It is a different. For the different central metal atom, the total number of coordination sphere, coordination isomer, it is a possible. That is a coordination number of that compound. That is a 6. It is there. So total number of isomers we will have, that is a 6. The other isomers, one more I can draw, that is a CR, it is a having NS3. So we are exchanging with the cyanide, that is a, if it is a 5 and this is cyanide 1. Cobalt, it is a having a cyanide 5 and NS3 1, it is there. So this way we can exchange the number of ligands from one central coordination sphere to the another coordination sphere. This formula, it is very important. You can use this formula to find the number of isomer directly. So question, it is a given, that is a match the following list 1 to list 2. It is a given the complex, it is a given, and type of isomer, it is a possible for the complex. First, it is a given, that is a linkage ambidentate ligand, it is there, that is a NO2. NO2 can be formed, NO2 can give a linkage isomerism, that we can say it is a second option is a correct. For this, it is a sulfate and pair, it is there, we can say it is exchange of ions can be possible, then we can say it is a, and this is a ionization isomerism, it is there, and this is a having a 2 complex, we can say coordination sphere, it is a 2 coordination sphere, it is there, this is a 6, this is also 6. So we can say coordination isomer is a possible. For this, we can say it is a hydrate molecules are there, we can say it is a solvate. Hydrate isomer is also known as a solvate isomers, that is, we can say first it is a match with the second, first it is a match with the second it is a third, C it is a 4, C it is a matched with a 4, and the D it is a 1, that is a first option is a correct for this question. Next, it is a stereoisomerism. Stereoisomerism, it is a, it can be possible, that is a, it is a GI or OI. Now for GI we know it is a different yeah, the different position of atom or group of atom. atom or group of atom in a space. So that we can set as a relative position of atom or group of atoms would be different. Now, in case of GI tetrahedral, so let's see first of all that optical isomerism. Then we will discuss about the different optically active compounds. What are the optically active compounds? Those compounds which can rotate the uh, plane polarized light that we know. If plane polarized light it is rotated by clockwise or anti-clockwise, then we can say that that compound it is a optically active compound, and it is known as a optical isomer. So optical isomer is what that which is having a case of this coordination complex. We can say those which does not have POS. If complex is not having a POS, then we can say it is a optically active complex. Now, in case of coordination number 4, there is a two possibility. In case of a coordination number 2, there is a two possibility. Either it is a tetrahedral or either it is a square planar. If it is a tetrahedral, we can say GI it is a never possible. Never it is a it can never show GI. As we know it is in case of tetrahedral. In case of a tetrahedral, the relative position of a ligands 1, 2, 3, even though ligands are different, we can say the relative position it is always same as the distance between the angle it is always same, that is a 109.5 degree. So it is a always same distance between the all the ligands to each other. That's why it is a there is no relative position difference we can get. In case of a square planar, it can show optically active compound. In case of a tetrahedral, it is a possible. Square planar optically active, it is not possible as it is a having a POS. POS is there, that's why it is a it cannot show the optically active optical activity. So GI it is a GI in case of a square planar, as a tetrahedral cannot show the GI. So we are starting with the square planar. Square planar complex of a type that is a M, A2 and B2. It is a it can show this all the types of square planar can show the optically active sorry that geometrical isomer it can show. So in case of a first it is a A2 B2. So M metal it is a form it is a connected with the 4 ligand that is a AA and BB. So it can show it as what cis type and trans type AA and so A it is the same side and opposite side. So this is a one out of them it is a cis and another one it is a trans. Similarly we can draw for other also, that is a cis and trans. For this it is a 3 isomer is a possible for the MABCD, and it is a what is the A B and AA. So AB it is a unsymmetrical ligand. Unsymmetrical ligand it is if AA it is a type of ligand is given, then we can form that is a it is a symmetrical type of ligand. So this is GI in the case of a square planar. Next it is a octahedral complexes. Octahedral complexes like MA4B2, MA4BC, and this it is a it can show the geometrical isomer. For example, this it is a given NH3, 4 NH3 it is there, and 2 chlorine it is there. So this we can say here it is a octahedral complex it is there. So this is the octahedral complex where we can say here it is a, this is the one geometry we can form. Next we can say here it is a relative position of chlorine. It is a anti of extreme at a extreme position, that is a, in case of a octahedral, that there's a two type of position we have, A, B, C, D, E and F. So there is a two type of position, that is a one which is having a 90-degree, another one which is having a 180-degree. So this type of two type of position we can see observe in the case of octahedral. Here chlorine it is at a 180-degree. Other way one we can draw, that is having a that it is a 90-degree. So relative position is changed for this chlorine. So these are the geometrical isomer of this complex. Next it is a Ma3B3 type of a complex exhibitor, meridian and facial type of a isomer. So what is a facial and meridian? When a metal complex it is a forming with a ligand three ligands it is a coming on adjacent position, then it is known as a facial type of a isomer, that is a, this is known as a facial type of isomer. Next it can show another isomer, that is a meridional. When it is a ligands are at a, one it is at a extreme, another two it is at a adjacent, then we can say that this is the meridional. So this is a meridional. Meridional. So this is the two types of isomers in the case of Ma3 and B3 type of complex, where it is a two types of isomer. It is a possible one, it is a facial and meridional, either we can say meridian. Okay, next it is a type of isomer, that is a, so these are the total list of all the geometrical isomers we can have, that is a geometrical isomer for the A B C D E F, it is a given. So it can show that is a total 15 in case of this all we can remember. So from here it is a, this it is a there, A4B2, A4BC, A3B3, next A3B2C, A3BCD. So these all are the for a octahedral complex. This is for the octahedral complex. Octahedral complex. Next it is a type of isomer, that is a optical isomer. So optical isomer which is having a coordination number 4, that if it is a coordination number 4 it is a given, that means it is a, we are talking about tetrahedral. Tetrahedral complex only can show what, that is a optical activity. Square planar cannot show the optical activity. So tetrahedral के केस में that is we can say here it is a M A B C D. If all the ligands are different, only we can have a optical activity. For example, this it is a platinum which with a amine aqua. This is a chlorine, chlorido, and nitro. So then we can say they have a optical activity. Next is a optical isomer or generally provided by the octahedral coordination in the complexes having a bidentate or a polydentate ligand. For example, this one. In the all cases, we can say this can show optical activity. So platinum with a 2 chloride and 1 it is a En it is there, 2 En it is there. Since En it is a symmetrical in nature, this is a symmetrical in nature. So this can give a what? It's mirror image which is not a superimposable. One another way we know that is a non-superimposable mirror image are also a optically active compound. So from here we can say this is a complex which is a non-superimposable. So if we make this complex like to get a non-superimposable, that is a unsymmetrical we can make. So the mirror image of this, now it is a non-superimposable. Now it is a non-superimposable, that we can say chloride here it is there, En it is there, chloride. So this is a what enantiomer pair. If it is a mirror image of each other and they are not superimposable, then we can say they are known as a enantiomer pair. Enantiomer pair. This is a enantiomers pair. We can say here it is a given. So optically active compound it is a formed by the bidentate or a polydentate complexes. Next it is a topic, it is about the effective atomic number. Effective atomic number, that is a En value, it is a, so it is a total number of electron which is available at a central metal atom. At a central metal atom, how many number of electrons it is remaining after the complex formation, that is known as a effective atomic number. So effective atomic number of this it is a complex, it is a given. So it is given by this formula, that is a Z metal, that is atomic number of metal minus oxidation state of a metal plus 2 into the coordination number. Since the coordination number, if it is a 1, means it is a 1 number of a coordinate bond it is a formed. So one coordinate bond, that means it is a giving the 2 number of electrons to the metal. So that's why it is a plus of a 2 into. So we can find that as a first of all oxidation state of this coordination complex, that is a, it is a 4 minus, that means it is a 2 plus. So coordination number of this it is a 6. The oxidation state of a complex it is a plus 2. Now we can say it is a EAN value, it is a what? EAN value it is a Z atomic number 26 minus the oxidation state of a compound it is a 2 plus the 2 into coordination number it is a 6. So we are getting what? 24 plus 12, that is a 36. So in case of EN value, It is a Sedgwick gives a rule. Sedgwick gave a rule one, that is a, if a complex is a forming a complex is a formed with the en number which is a near to the, that is a inert gas atomic number. If it is a forming inert gas atomic number, for example, for the 3D series, it is a 36, that is a krypton. Next, it is a xenon, that is a 54 for the 4D series. So we can say this for these elements which is belonging from the 3D series, if it is achieving the En well effective number of electron, that is a 36, then it is a more stable than the other complexes. So it is according to the Sedgwick rule. Either we can say it as a EAN number rule. So EN number, it is not followed in the all the complexes. It is a generally it is a followed for a metal carbonyl, for a metal carbonyl. Generally, it is a followed for the metal carbonyl. For example, NiCO4. So you can find the En value of this complex. Effective atomic number of a complex. So nickel, it is a what? It is a Z value. It is a 28. So 27. We can say it as a. So it is a 28. Okay. Next, it is a total number of oxidation state at this metal. It is a 0. Oxidation state of this metal, it is a 0. So metal have a oxidation state 0 only in the case of what? In the case of a metal carbonyl, we can say it as a 0 oxidation state. It is a plus 0 minus, it is a minus, it is a 0 plus of 2 into total number of a coordinate bond, it is a form, that is a 4. So we can say it is a 28 plus 8, that is a 36. So we can say here it is a, this is a following the Sedgwick rule, that is a EAN, effective new atomic number rule. So the metal carbonyl, that is a, from the NCERT I have taken this. NCERT, it is a given this all the metal carbonyl, which is very important for the exam purpose. So this is a tetrahedral complex. Next, it is a FeCO5, that is a pyramidal trigonal bipyramidal. It is a, if it is a CO2 CO whole 8, it is a given, then it is a complex. This is, it is a, and geometry, it is not defined, and this is not in our syllabus. Next, it is a CROC a whole 6, that means it is a having a 6 carbonyl is there, then it, we can say it is a forming about octahedral. So whenever there is a 6 coordination number, it is a given in the all the cases, it is a octahedral. This is a Mn2 CO whole 10. In this case, it is a metal bond, it is there. So metal bond, you should remember this. In case of Mn2 CO whole twice, it is a metal bond, it is there. In case of this also, it is a metal bond, it is there. So the question is asked like the how many types of a CO it is there. So CO which is bonded with the one which is directly with the metal. CO which is directly bonded with the metal. Other CO which is forming a breeze between the two metal. So basically there is a two type of carbonyl, one which is a forming one bond, another which is a forming a breeze between the two metal atom. Question it is asking in case of Mn2 CO whole 10 and CO2 CO whole 8 structures have a metal linkage. Yes, they both have a metal linkage. Terminal carbonyl group, It is there. Brazing group, it is there or not. So in case of amine complex, it is not there. Not there in case of this one. But cobalt, it is having a bridge ligand. Metal in this oxidation state of this metal, it is having a zero oxidation state. In case of a metal carbonyl, oxidation state of a carbonyl metal, it is a zero. That is also true. So we can say the correct answer from the option, it is a what? A, B. A, B, D, it is correct. Next, the bonding in the coordination compound. So basically, it is a bonding started from the first. It is a complex structure. It is explained by the Werner theory. Werner theory, it tells about the primary valency, secondary valency, means ionizable and non-ionizable ligands. It is asked. The second, it is a theory, that is a valence bond theory. So valence bond theory, it is all about, we can say, it is overlapping. It is overlapping between orbital and ligand lone pair. So orbital, it is empty. And valence bond theory, it is also involvement of hybridization. It is there. Hybridization, it is also involved in case of VVT. Next, it is we can do, that is some hybridization we can write. First of all, if it is a SP, then we can say it is a linear, and it is similar to the chemical bonding which we have done. If it is a sp2, if it is a sp2, then we can say here it is a trigonal, planar. If it is a sp3, then it is a tetrahedral. sp3d, trigonal bipyramidal, trigonal bipyramidal. If it is a sp3d2, it is octahedral. So in case of a coordination number 4, it is important, and coordination number 6, it is important. Coordination number 6, it can have two types of hybridization, and coordination number 4 also have a two type of hybridization. If it is a coordination number 4, it can be have two possibilities. It is dsp2, either it is a sp3. If it is a sp3, it is a tetrahedral, and if it is a dsp2, that means it is a square planar. It is a square planar. But in case of that, we can say here it is a coordination number 6, always a form octahedral. It can, hybridization can be different for the different complex. For example, it is a d2, it is a d2 sp3, either it is a sp3d2. If it is a sp3d2, then it is known as a outer orbital complex. If it is a d2 sp3, then it is known as a inner orbital complex. Inner orbital complex. Okay, later on we will see that as an inner and outer orbital complex. Here it is a given. First, it is a NiCO 42 minus. So it is a 2 plus. It is a, so minus. Okay. So this is having a tetrahedral. So that we will find this is a pyramidal, bipyramidal, trigonal bipyramidal. That is a TBP. Now, how to find the inner and outer orbital complex. So to get this, first of all, so let's start with the first example that is given here. So Fe, it is first of all Fe, we will find the oxidation state of Fe. It is Fe2 plus. So Fe2 plus it is there. So what is the configuration of Fe2 plus? That is a 3D8, 3D6. So this is a 3D6. If we draw this orbital diagram configuration, then it is what? This is a 3D6. So d orbital it is a 5. 1, 2, 3, 4, 5, 6. Next it is a 4s is there, which is empty. Next it is a 4p, it is there. Now it is a given there. Here it is a cyanide, which is a strong field ligand. So what is a strong field ligand and weak field ligand? That we will later we will see. That is a strong field and weak field ligand. So if strong field ligand it is there, we will do the pairing and the orbital. So if we do pairing of a electron, then we can see here it is a two electrons will be paired and it will form what? That is a, after pairing we will get two orbitals vacant. Now if inner orbitals are free for the overlapping, the inner orbital will we will take, that is a what? 3D orbital we will take. And how many total orbitals we need for the overlapping? That is a number of ligands. If we are having a 6 number of ligands, the monodentate we are talking. So if 6 ligands are there, we can say it is a 6 number of orbitals we need, the 2, 3 and total it is a 6. So for the 6 total hybridization, total orbitals 6 orbital, it will mix and it will form what? D2sp3 type of a hybridization. So D2 sp3 type of a hybridization, it will be what? Octahedral. And others information we can say it is a, as it is a inner orbitals are used, then we can say it is a inner orbital, inner orbital complex. Second, it is a, one more thing, it is there, high spin and low spin. If number of electron pair, it is a, if electrons are getting paired, then we can say it is a low spin, low spin complex. As it is a spin spin, total spin it is a very low after the pairing. And if pairing it is not done in the case of a weak field again, then it is known as a high spin complex. Okay, let's see the next example, that is a COF6. COF6 3 minus. In this case, cobalt it is having 3 plus configuration. So configuration of this, it is what? This is a 3D. So cobalt it is a what? It is a 4s2 3D 7. If we remove a 3 electron, that is again it is a 3D6. So it is a getting a 3D6 orbital. So 3D6 orbital it is a what? We can say here it is a having 6 electrons are there. 6 electrons are there. And fluorine, as it is a what? Weak field ligand. So weak field ligand does not give a pairing. So pairing will not occur. We can say the 6 electrons will be there like this. And outer orbitals, like this is a 3D. Next it is a 4s, 4p and the 4d. Since it is a See, we need a what? 6 vacant orbital for the overlapping. 6 vacant we need. So from here we can take only, there is a 6 orbital we need, that is a sp3d2 type of a hybrid orbital we will get, that is a 6 orbital we will get. Okay, so these are the having, this is orbital which is having a vacant orbital, and the 6 fluorine will give its electron pair. So 6 fluoride will give its electron pair to the this hybrid orbital, that is a sp3d2. Now it is a sp3d2, then we can say it is a high spin. First of all, it is a outer orbital complex, outer orbital complex. So why it is a outer orbital complex? As the outer orbital are used for the formation of a hybridization, then we can say for overlapping, and it is a high spin. As a spin, it is a very pairing it is not done, then it is a high spin complex. Next, it is a, we can find the total number of unpaired electron, that is a 4 unpaired electron is there. Now we can find the mu value, that is a square root of 4 into 4 plus 2. We can find the magnetic moment value also. For any complex, we can find all the things of this. Next thing, it is a magnetic property of a complex. So magnetic property, if it is having a number of unpaired electron, if unpaired electron it is there, then we can say it is a paramagnetic. Paramagnetic if n it is not 0. If n it is not 0, then we can say it is a paramagnetic species, and if it is a 0, then we can say it is a diamagnetic species. So this is the same as a what? D block complexes, D block compounds. Next, it is a crystal field theory. So what is a crystal field theory? So basically, VBT was unable to explain the proper geometry of a compound, and the color of a complex, it is also not explained by the VBT. So that it is a CFT will come, that is a crystal field theory. So what is a crystal field theory? So in this case, we can say the central metal atom it is there, and ligand it is there. And central metal atom, it is considered as a positively charged point charge. Positive point charge, it is a considered, and ligand it is a considered, if it is a negatively charged, then it is a considered as a point charge. And if it is a neutral ligand, in case of a neutral ligand, it is considered as a dipole. Now they will interact to each other. Now the ligand will approach the central metal atom, and due to that, the variation of energies of d orbital, basically this is a degenerate orbitals, of this is a degenerate orbitals. So this is a d orbitals, and we have 5 types of d orbital it is there for d subcell. So how many orbital it is there? That is a dxy, dyz, dzx. So these are the 3 orbitals which is having its lobes in between the axis, So between the axis, lobes come. So when lobes are coming in between the axis, then these are known as a T2z orbital. And the other type of d orbital, it is a what? Dx square, y square, dz square. So this is the set of orbital is known as the what? It is a, in this case we can say it is a lobes lies on axis. So in case of a dx square, y square, it is a x and y. Dz square, it is a lobes will lies on the z axis, and another ring it is there. So these are the two types of d orbital it is there. So this set of orbital it is known as a easy orbital. This is a T2Z, where a 3 orbital it is a of a same type when it is a lobes are lies between the axis, and another it is a when the lobes are lies on the axis, then it is known as a easy orbital. So basically, when it is ligands are approaching, first one central metal atom it is having a, it's a field, that is a crystal field we are talking about. The, it's a field it is there, that is a charge, positively charged it is there. This is a positively charged metal it is there. So when ligand is approaching, its energy first it is increases in the presence of a ligand. So field energy of a d orbital first it is increases, and it is split into two part. It is splitted into two parts, and the central line it is known as the barycenter, from where it is energies of the splitting of T2Z and EZ is T2Z and EZ is calculated. So T2Z it is a get energy it is a decreased, for EZ it is a energy it is a increased. So the increased energy it is a given also. From the barycenter it is taken as a positive and negative. So what is a delta O? Delta O it is known as a octahedral splitting. So in case of a strong field, octahedral splitting, so octahedral splitting it is more for the splitting, it is more for the SFL, then the WFL. In case of a WFL, splitting is a less, and in case of a SFL, it is a splitting will be more. Next, in case of a in case of a tetrahedral, splitting will also there. That is a one metal, central metal. It is there having a positive charge. So around there is a electron density. Is there. There is a field. It is there. When it is a ligand is a coming, its energy will increases first of all, and there is a splitting of d orbital, and in between that there is a barycenter. The splitting is known as a what? That is a delta t, which is known as a tetrahedral splitting. Tetrahedral splitting it is given as a, it is from barycenter it is increased for the T2Z. So it is a basically reverse of a octahedral. In case of a octahedral, EZ is energy is increased. In case of a tetrahedral, T2Z energy is increased. The energy gap it is also reverse we can say. Next it is the question we can see it is first it is so let's see first of all the splitting it is decided by the field strength of a ligand. If it is a highlight, it is there. Next it is a carbon donor, sulfur donor. This all are weak field ligand. This all are what? Weak field ligand. The what are the strong field ligand? That is we can say this all are strong field ligand, where it is a carbon, nitrogen donor it is involved. Carbon and nitrogen donor. So they are a strong field ligand. They are a strong field ligand. They have a strong they will have a strong large splitting in the case of that octahedral. Okay, next we can see some complexes, the examples. Either we can see the filling of electrons first of all. In case of D1, D2, D3, it is SFL or WFL. The filling it is always basically it is always same. This is a T2. We are talking about the coordination number 6. That is a case of octahedral. So D it is a T2Z and it is a EZ. EZ it is having two orbitals. T2Z it is having a three orbital. So D1 it is a one electron it is there. In case of T2G it is a in case of a D2 it is a only two electron is there. In case of a D3 it is a three electron. In case of a D4 so it is a D1 D2 D3 D1 D2 D3 D4. So in case of a D4 there is a possibility of pairing or not pairing, that we can say pairing is done or not, that is decided by if it is a SFL it is a pairing will be done. If FSL it is there, SFL it is there, then we can say pairing will be done and it is this. If it is a WFL it is there, in case of a D4 pairing is not done and it is a D4 where electron gets come into the easy orbital. So in case of a D4, D5 and D6 it is all having a same. So this way we can do the configuration. Next, in the case of coordination number 4, we can have a two type of configuration. One it is easy, two type of orbital, one easy and T2G, EG and T2G. If one electron it is coming, there is no problem. 2, 3 it is a case of a 2 it is a two electrons will come. In case of a 3 electron there is a possibility of pairing or not pairing. So it depends on the strong field ligand or a weak field ligand. If it is a strong field ligand, we can say pairing will be done and the third electron will come in the easy it is given. It is a easy and this is a T2Z. So this way we can do the configuration of complexes. So this question it is a given. So given below the two statements, first of all, it is a both complex, it is a this and this are octahedral but differ in their magnetic behavior. So the complex, if I see, it is a first one cobalt, it is a first cobalt it is a given in the 3 plus cobalt in 3 plus it is a 3d6 and second complex it is a given, that is a cobalt 3 plus, same it is a given, but here it is a difference it is what the amine it is what strong field ligand, fluoride it is a SFL, so WFL, weak field ligand it is there. Now we can say here it is a in case of a amine it is a weak field ligand it is there. In case of a weak field ligand octahedral it is there. So splitting is like this, T2Z and EZ. In case of a strong field ligand, the pairing will occur. The electrons, the 6 electron will be filled like this. And the inner orbitals will be used for the hybridization, that is D2 sp3. D2 sp3 is in case of NH3 ligand, NH3 which is a SFL. Now it is in the case of a fluoride, we know it is a what weak field ligand. As it is a weak field ligand, it is there. So if it is a weak field ligand is there, we can say the pairing will not occur. Pairing will not occur, and 6 electron will be filled like this, 5 electron, then 6. So how many unpaired electron we are getting? So there is a n value, it is a 4. Here it is a unpaired electron, it is a 0. Since it is a talking about the magnetic behavior, different in the magnetic behavior, that is a true statement. As it is a having a both complex, it is a octahedral, but it is a magnetic behavior, it is a different. Statement second, it is a given. This is a diamagnetic, whereas the cobalt fluoride, it is a paramagnetic in nature. The light of a above statement shows the correct answer from the options given. So it is a given that we are having a D2sp3, which is having a n is equal to 0. That means a magnetic moment value, it is a 0. It is a diamagnetic, since it is a number of unpaired, it is there. Then we can say it is a paramagnetic in nature. So this is a correct, we can say. Statement first and second, it is a both are true. That is a both statements are true. Next, it is a given this. Similarly, in the similar way, we can find all the things, that is the inner complex, outer complex. Next, it is a factor affecting the splitting energy, that is a delta. So delta, it is what? Splitting energy. So strength of a ligand, it is a first we can check if it is a FCFSC value is a more in the case of SFL as compared to the WFL. So CFSC value, it is what? So it is a CFSC value. So what is a CFSC value? It is a crystal filled splitting energy. If it is a crystal filled splitting energy, it is a more in case of SFL. So strength of a ligand will be more for the SFL as compared to the WFL. The splitting will be more in the case of a SFL. Next, it is a oxidation state of a central metal atom. If central metal atom oxidation state is a more, then we can say it is a directly proportional to what? That is a CFSC value. It is a directly proportional to the oxidation state of a central metal atom. Next thing, it is a transition series. If it is a lies between, so if central metal atom, it is a belonging from the 5D, it is a having a more CFSC value than the 4D, then 3D. Next, it is a geometry, number of ligands. If number of ligands in the case of a square planar, it is a more, then octahedral, then tetrahedral. So splitting of a square planar, it is a high. So this is a splitting CF SC value. CFSC, it is highest for the square planar, then octahedral, then tetrahedral. And this relation, it is very important for the exam purpose. It is can be asked in the exam. The square planar, it is 1.3 times the octahedral, and the tetrahedral, it is a 4 by 9, it is times the octahedral. Okay. Okay, next thing, it is we can see the CFS value calculation. So how to find the CFSC value calculation? How to find the CFSC value? So to find this, we can do the calculation from here. That is in case of octahedral. In case of octahedral, in case of octahedral, it is about the number of minus 0.4 into number of electrons in the, that is a T2G, plus that is a 0.6 delta O, 0.6, that is the number of easy electrons into delta O, plus x into x, where it is a x is a what? Number of unpaired electron, that I can say here it is a n into the pairing energy, it is a, this is a pairing energy, the pairing energy which is will be given in the question. Similarly, CFSE value for the tetrahedral, CFSE value for the tetrahedral, it is a minus of a 0.6 number of easy electrons plus 0.4 times number of T2G electrons into delta T plus X into the X means it is a number of unpaired electron into the pairing energy. So by this way we can find the CFSE value for the both complexes. So if we can find this one, then we can say the first thing that is this one. Okay, the more one thing that I want to tell you, that is a color in the complexes. Color in the complexes, we can see first of all the color in the complex. The color in the coordination complex, it is due to the DD transition. Basically, transition between the electron can be transit from the T2G to EG. So if electrons are getting transferred to the from T2Z to EG, there is a released energy will be there, that is known as a, we can say it is a, if it is lies between the visible range, then we can say it is a light will be colored, color will be observed. So one thing it is if we draw the color, complementary color it is there, that is so if it is a color which is absorbed, then if it is absorbed color will be violet, then it is a observed color, observed, it is a observed color will be yellow. That means this is known as a complementary color. So basically it is a if it is a observed color, it is a, we can say it is a absorbed color is a violet, then it is a observed color will be what, yellow. It is a blue is a absorbed, then it is a orange will be visible, and if it is a red is a absorbed, then we can say green will be the visible. So since it is a if it is a difference between this, it is a delta E, we can say the energy level of this T2G and EG, T2G and EG. If it is a difference as a more, we can say energy. So the splitting, it is a, it can be decided by what, the splitting energy. The delta O, it is a directly proportional to what, the delta E, and the delta E, it is a absorb energy, and absorb energy is also, it is a SC by lambda absorb, that we can say if delta O means octahedral splitting. If splitting is the more, we can say absorb energy it is a more, and lambda is a less. So absorb lambda it is a less. Now we can check for this complex, that is a, we have a question that is this one. So the correct order of the wavelength of a light absorbed by the following complex is a, so that we can check the order of absorbed complex. It is decided by the what? The delta O. Delta O, since it is directly proportional to the energy absorbed. Energy absorbed we can find with the help of this. And delta O, it is a more for the strong field agent. Strong field agent, it is having a more than the weak field agent, delta O value. Now we can check for the strong field ligand. We have a NS3 which is a strong field ligand, and cyanide it is also a strong field ligand. So in case of this, we can say the first one it is a more stronger than the second one. The both it is having a same oxidation state, that is a, we can see here it is a both it is a having a same oxidation state, that is a 3 plus 3 plus cobalt, it is a 3 plus cobalt, it is a 3 plus. Now it is a cyanide and NS3, it is a cyanide is a more stronger field ligand, so it is a stronger field ligand. Stronger field ligand will have a less lambda value, so this is a stronger field ligand. So first we are checking that delta O. If delta O it is a higher, lambda absorb will be less. So delta O it is a cyanide, it is a more than NH3. Then out of a H2O, in case of a C and A, it is a C, it is a for the tetrahedral. Either we can say this is a coordination number 4. If coordination number it is a 4 and here it is a coordination number 6. So the splitting will be more for the what? Octahedral. So octahedral splitting will be more. So I can remove this since it is for a splitting of any of a complex. So we can say here it is a, for C it is a, the the splitting is a more for the what? That is a coordination number 6, it is given. So for D, it is a splitting will be more than the C. So what is the order of splitting? That is a cyanide in the case of a B, B A and D C. It is a splitting of a that T2Z and EZ. Now it is a we can compare the value of a lambda absorbed, that is a light it which is absorbed is, so C it is the highest since it is a least splitting is there, then it is a D, then A and B. So this is our lambda absorbed value for this complexes. Next we can say that is a application of complexes. So some complexes are very useful, like Fe3 ion in the group third. It is identified as a, this one is a, which is having a blood red color. Eh, So this is a test for a what? It is a thiocyanide. Second is in the electroplating of a Ag, large amount of a silver are held as a complex, which is this one. So this complex is formed in the case of electroplating of Ag. Next is a hemoglobin complex. It is formed, which is a complex of Fe2 plus. Chlorophyll, it is a complex of Mg2 plus. And vitamin B12, it is a complex of CO, cobalt 3 plus. So these are very useful and this is a very important also. So this is our coordination complex. So thank you everyone.